put to other participants most during your that's
Restate of the LSST AGN science collaboration.
Right. Yeah. Just my point this. How do I hit this?
doesn't work.
Oh, yeah, I don't think so. I can just use a button on the computer.
Okay, inside.
He's never
Yeah,
heard.
that might be actually better for.
I can press buttons on.
Yeah,
the computer.
while I'm figuring this out, why don't we just start without just this fancy thing?
Okay, fine. And you can just advance the slides.
Yeah, I'll do
Okay,
it for you.
great, thanks. Okay, go back to the first slide. Great, thanks. So today I would like to briefly review the LSST AGN science collaboration, focusing on its activities as of 2023. This is an exciting time. We're just, I guess, 1.5 years away now from actual Rubin Observatory operations. Today, I will only be hitting some of the recent highlights of the activities of the AGN Science Collaboration. So my apologies in advance if your favorite activity is not somehow covered in depth. And here I am aiming to give all attendees, including new AGN-SC members or people who aren't members but are interested in a common broad understanding so that you can appreciate further all the great science talks that are coming. So the AGN Science Collaboration, of course, is broadly interested in all aspects of the AGN. As you can see in this diagram, ranging from the black hole to the accretion disk corona, out to the emission line regions and the obscuring materials, jets, host galaxies, and co-evolution with host galaxies and large-scale structure connections. So we have people working on a broad range of topics. Next slide. Yeah, so the overall goals of the AGN Science Collaboration are to maximize the AGN science return of the LSST, to give feedback to the project, which is very important, especially around now, to ensure excellent AGN science, and also to, of course, via outreach and education, to educate the broader community about LSST AGN science. Right, and so just for a very brief history, it's just a one-slide history. So the AGN Science Collaboration has existed since fall 2006. Here is, in fact, one of the emails. This, I think, was the very first email getting the science collaborations organized. And the science collaboration has always been by design. And here is, in fact, the original design document written by Steve Kahn back in 2005, December. It has always been, by design, distinct from the project and has thus never received direct funding from the project. And that, of course, has led to some real challenges. We still don't have any real direct funding, and I hope you will appreciate that when considering the level of services that the science collaboration can provide to you. Next slide. Yeah, so here is the current membership. We currently have 181 members. We are still rapidly growing. Over the past year, we grew by 37 new members. That's a 20% growth year over year. The previous year was about 30%. So maybe we're converging, we'll have to see. We have 168 associate members and 13 full members. Here is a breakdown of the largest national memberships by country. And with this number, please forgive me, I can't even remember everybody who's on. I can't hold all 181 in my head anymore. So my apologies if I ask you if you're a member and you say, oh, I already am, because I do my best. Yes, okay, so membership applications are certainly still welcome, even from people who lack data rights. The application instructions are available on our webpage, and It's important to note, however, that AGN Science Collaboration membership does not by itself confer data rights. Now, for people in the US and Chile, you automatically get data rights by virtue of the various arrangements, and that is true for a limited number of other international organizations. But beyond that, there is this formal in-kind process by which you get data rights. As of 2019, we have an organized AGN Science Collaboration Charter. I'll show some slides from that in just a minute. And we have also received formal recognition under the Science Collaborations Federation Charter System, which gives us some responsibilities and some rights, regarding interactions with the full project. Here is the overall organization adapted from the AGN-SC Charter. There are currently 2 co-chairs, Gordon Richards and myself. We have a number of kind of organizational panels that keep the various functions of the AGN Science Collaboration going. Some of these are still being set up to some extent. And then we also have a number of science subgroups, people who are working on various interesting scientific topics. Also, I want to note that we have a couple of coordinators of this important international in-kind contribution process. Sebastian Honig and Paulo Coppi are serving on that presently. We have a liaison to the Survey Cadence Optimization Committee. This is a very important process that's currently ongoing. I'll say more about this in a minute. That is Franz Bauer. And we also have 2 members who are serving on the broader Rubin Users Committee. That is Qingling Ni and Ashley Villar. Right, so here is just one way that we're trying to get a little bit more organized. We are currently getting a project posting system set up. Roberto Asaf and Chris Carroll are leading the work on this, to my understanding. Am I missing anyone else, or is that correct?
That is correct.
They're doing the heavy lifting on that, and perhaps they can tell us more about that in a minute. This aims to provide a way for people to post projects and encourage collaboration, but there is no intention of cordoning off projects. You can't somehow say, well, I own all the blazars, or I own all the binary supermassive black holes and you can't touch them. There's no cordoning off of things like that. We are also, so this is using a free open source software called Open Project. PIs will apparently be submitting new projects through a Google form to a publications committee that is currently being set up, and we have some volunteers for that. Next slide. We also have a roadmap document. This defines and prioritizes in a semi-organized way the AGN Science Collaboration activities needed to prepare for Rubin operations. The most recent version of this was presented at last year's meeting. And so I encourage you all to check that out, and work is ongoing to address many of the roadmap goals. So now I want to move on to talk about some recent and ongoing activities. Next slide. So first of all, how do we communicate with each other? Well, of course, we have regular full AGN Science Collaboration and subgroup telecons. We also, for the past several years, have had remote and/or in-person meetings. We've been doing those annually. Next slide. I want to go back and forth. Here are just some nice photos from, in fact, I think this may be the last time we actually had a proper in-person meeting, back in 2000 January. This was led by Ohad Shemer, was held in Grapevine, Texas, as part of a AAS meeting. And then for the past several years, we have been meeting over Zoom. We had intention of actually having another in-person meeting, but it got canceled due to COVID. And then we decided, well, actually this remote thing works pretty well because it doesn't cost any money, and we have no money, so that's a perfect match. Okay, so we've had a number of remote meetings, and I think those have been quite successful. Yeah. Right, great, thanks. We have, of course, an email list that you can post to as you wish. We have a community, and we also have a Slack channel. Okay, jump ahead. Yes, okay. So now I want to say a few words about the AGN Science Collaboration and the relevant ongoing survey cadence optimization process. So, as I've already mentioned, there is this important survey cadence optimization process currently ongoing. The goal of this is to determine how to observe the main survey and how to spend 10 to 20% of Rubin's time, a substantial amount, on these mini surveys. All of this, of course, is essential for many AGN science cases, ranging from AGN selection to general variability studies, the studies of supermassive black hole transients, and so on. And there have been a couple of very important reports, which if you have not read, are well worth your time to read. There is the stock phase 1 recommendations, which was perhaps briefer. Here you can actually summarize the main results here. I'm not going to read these out to you right now, and then there is also just more recently a phase 2 set of recommendations that has just recently been released. These are more substantial and start laying out real points on how the survey will actually be executed. So if you want to know exactly what is Rubin going to do, how does that fit into how I want to do my AGN science, this is well worth your time to read. Just a couple of key points, and this is by no means a complete summary, it's an extensive document, but a couple of key points that are worth noting. For example, the wide, fast, deep main survey is going to have a half sky rolling cadence. So what that means is you'll have the entire sky that's accessible to Rubin at any given time. They're not going to try to observe that entire area. They're going to observe half of it much more intensively. And the aim there is to improve sampling in the 3 to 5 day range, which is very important for a variety of science cases. For example, the supernova folks are very keen on that. Of course, the AGN people don't get to decide exactly how the cadence is all by ourselves. We have to, cooperate with the dark energy people and all the other science collaborations, and we try to find something that is mutually acceptable. So anyway, that's one thing that's very important. You should think about what that's going to do if you have interest in studying AGN variability, for example. Also, another important point, and I think this is good news for us, I believe, is that 5 to 7% of Rubin's time they have dictated from the heavens will be spent, on the deep drilling fields, and that's, I think, good news for us. There's been a lot of preparatory work in the deep drilling fields on AGN science. I'd argue the AGN science is one of the leaders in the deep drilling fields, in fact. And so this should allow excellent, deep, and densely sampled coverage for AGN studies in the 5 deep drilling fields labeled down here. And I'll say more about those a little bit later. Okay. Is that the next slide? I can't. Yes. Okay. That's the next slide. Thanks. Yes. So then, what is the AGN-SC status relative to this cadence optimization process? Well, we have delivered 8 cadence notes, in addition to earlier white papers we delivered back in 2018, as well as 4 coded metrics, as well as in fact, I believe 3 journal articles. Next slide. I just want to point these out. So here are a set of cadence notes. These are 6 of the 8 that the AGN Science Collaboration delivered, stating what we would like the cadence to be like. And these are being considered by the overall Survey Cadence Optimization Committee right now. Next slide as well. Yeah, and here, I want to just show you a couple of the papers. So there's been papers that the AGN Science Collaboration has led on blazar variability, on accretion disk reverberation mapping. Sorry, next slide. And okay, and there's been another one just recently led by Bozena Cherny. I won't go through this one in detail for limited time, but basically she investigates doing a reverberation mapping of emission lines using the Rubin filters. And she argues in this paper that you actually can, in some regimes, recover useful emission line reverberation mapping, even from the broad filters. And you can see her paper for more details. So I want to go back now 3 slides to finish that previous one. I jump around a bit in how I present my slides. Yeah. One more back. Thank you. Yes, okay. We also, of course, continue to communicate with the Survey Cadence Optimization Committee via community input forms. I recently submitted one of those on the deep drilling field, laying out the AGN science collaboration desires there. Meetings with Lynn Jones, who's doing a lot of the heavy lifting on simulations work, as well as feedback to Franz Bauer, who, of course, is an AGN Science Collaboration full member and is also heavily involved in the Survey Cadence Optimization Committee. And is hopefully, his job is to represent science more broadly, but clearly he hopefully has AGN science in mind. I will just mention that the AGN Science Collaboration members need to continue working through new operation simulations. Version 3 has just recently come out as part of the phase 2 recommendations. And you should be working through those to assess if those are going to allow your desired AGN science to be achieved. And that's best done, of course, with coded metrics that we've discussed on science collaboration telecoms in the past. And then, of course, it's also very important to continue coordinating with other science collaborations to push for mutually acceptable cadence solutions so that, for example, the supernova people are happy and the AGN science collaboration people are happy and nobody gets totally left out in the cold. And there have been very productive discussions, for example, with the dark energy science collaboration, in ensuring, for example, that a lot of the cadence is done in a mutually acceptable way. I'm going to go forward several slides. Yes, okay. So one back. Okay, right. So now I want to speak about gathering and analyzing key data for LSST and multi-wavelength AGN studies. And this is something where I think the AGN science collaboration has been a genuine leader in a variety of ways. And this goes back quite a while. In fact, Mark Lacey, who's here, yes, Mark is here, has, of course, gathered extensive Spitzer data in the deep drilling fields. And I think we're all going to be very grateful that was done when Rubin switches on, because that will be extremely helpful for selecting AGNs, characterizing AGNs, and so on. Today I'm going to focus on some more recent efforts. So another point to mention here is that we have recently in the science collaboration had a data challenge exercise. Here are the instructions for it. This was led by Gordon Richards and Weizhang Yu. And this was part of our general efforts to prepare students, postdocs, and others for LSST AGN science. 5 submissions were received to the data challenge, and these were competitively judged. Monetary prizes were awarded for those kindly funded by the LSST Corporation. And the data challenge data set, which I believe is primarily an XMM LSS and also maybe Cosmos, it has been made public with many access requests. So people are using that. There was also, I'll mention, a draft paper on some of the data challenge results led by Savik et al. And this, I am told, has recently been accepted. And you should be able to read about this shortly when it appears on arXiv. Also, we have done a lot of work doing AGN selection in the deep drilling field. So as soon as Rubin switches on, we have ground truth, well-validated, well-characterized AGN samples that we can start doing science with right away. And here is one example of a project where we have recently gathered substantial X-ray data in 3 of the deep drilling fields. Cosmos already has extensive X-ray data over 2 square degrees. We gathered these data at about a 50 kilosecond XMM Newton depth. And Qingling Ni and Chenting Chen did a huge amount of work cataloging all the X-ray sources. We have now 10,200 X-ray validated AGNs, as well as many X-ray groups and clusters in the deep drilling fields. We couldn't cover the full 10 square degrees, but we covered large amounts of the deep drilling fields. We covered half, almost half, and then about a third of each of those 3 deep drilling fields. And again, these are ground truth X-ray validated AGN samples that you can use to calibrate LSST AGN selection in the deep drilling fields, and then of course use the knowledge you thereby gain to scale it up to the full survey. We have also done a lot of work, very briefly, just recently in doing selection of AGNs based on radio methods, utilizing radio morphology, radio spectral index, and radio access, using these radio data sets. And this is, very useful as well. This is work led by Shifu Zhu. He has found now 1,815 radio AGNs. And the interesting thing, which is as expected from our knowledge of other fields, is the vast majority of those are not actually found via the X-ray or mid-infrared selection method. These are typically kinetic mode AGNs instead of strongly accreting AGNs that have been selected out. So that gives us another aspect of the AGN population. And then, of course, here are the mid-infrared AGNs selected from mid-infrared techniques. Okay, also, next slide. No, one back. There we are. We have also done a significant amount of spectral energy distribution fitting now in the deep drilling fields. We have, and this is work led by Fan Zhao, who is here, he did a huge amount of work for 3 million objects in the deep drilling fields, not all AGNs. He did all the AGNs and all the galaxies down to quite faint magnitudes. He uniformly selected and then fit spectral energy distributions in the deep field south, XMM LSS, and LISS1, 3 of the deep drilling fields. This allows improved source classifications, galaxies versus AGNs versus bursting and quenching galaxies, as well as measurements of galaxy properties like stellar masses, and star formation rate. So you have some post-galaxy information to look at galaxy black hole growth connections. And this goes quite deep, down to about 24th magnitude or so in the I band before the data start becoming limited. And there is a large publicly available data release on Zenodo for everyone to use to get ready for science of the deep drilling field. I will also mention then that there is another group based in the UK that has also done very valuable SED fitting work. In this case, they have focused on 711 luminous X-ray selected AGNs. And in this case, the work is focused on actually getting AGN properties from the SED fitting, like luminosities, obscuration, emission line properties, and host galaxy stellar masses. So it's worth using that as well. Okay, so now I'm going to end just by talking about some additional recent activities and news. So we have, of course, been also participating in the photometric redshift broad effort led by the Rubin Observatory project and data management team overall. And we have submitted some letters of recommendation saying, don't forget about the AGNs. These are the, don't forget that you need to use different templates for them. Galaxies don't work so well, and so on. And so, and I believe we continue to interface with this effort. We also have connections to LINCC, the LINCC Frameworks project. Neven Caplar is now a LINCC member, and I believe has agreed to serve as a liaison between the AGN science collaboration and the overall LINCC effort. So you can speak to him about that. Also, just a couple of other recent activities. We have several members on the Rubin Euclid Derived Data Project Working Group, and clearly that's becoming increasingly relevant. Okay, now that that's up in orbit, up in space, we have also 15 AGN science collaboration members involved in the data preview effort. We also recently had a nice training session on inclusive communication and leadership led by Alicia Shugart, who works as part of the Rubin project. That was very valuable. And then we are also coordinating with other AGN projects, for example, reverberation mapping efforts and X-ray missions like StarX and Athena, to try to be sure that all these missions fit together in a well-optimized way to get the most science for everybody. Here is just one example. I've been spending a lot of my time on this over the past 2 years. This is a mid-X mission that is currently undergoing a phase A mission concept study. We have there were 2 missions competing for 1 launch slot, so we have a 50% chance of this actually happening. And this mission carries an X-ray telescope and an ultraviolet telescope. Both of them are very wide field and very sensitive. They're mounted on an agile spacecraft like that of Swift. And so this would actually add daily X-ray and ultraviolet monitoring of the prime areas of the deep drilling fields for 2 years. What's written into the science program of this mission is intensive targeting of the deep drilling fields for a substantial fraction of the observatory's time, as well as other wider field surveys. So this has great prospects for interfacing very effectively with Rubin, and it would cooperate with Rubin for much of Rubin's operational lifespan. I will say also the AGN Science Collaboration regularly gives talks worldwide highlighting AGN science. Here are some examples of recent conferences and upcoming conferences where the AGN Science Collaboration will be presenting its science. And of course, we are happy to represent the AGN Science Collaboration at institutes worldwide, if that's useful to you. We also have had a significant amount of impact with outreach from our 2020, 2021, and 2022 summer meetings, which are all available on YouTube. There's 20 hours there, so if you don't have enough YouTube in your life already, 20 more hours there, and you can use that to, of course, learn about what people are thinking about Rubin AGN science, and there's a lot of useful technical information there. And so oftentimes when people write to me with questions, well, tell me about how this thing is going to work. I just point you to a YouTube video because it's all there with a nice half-hour organized talk. Okay. And then finally, we have a number of other outreach activities. For example, our colleagues in Serbia primarily led a nice workshop on AGN variability for students from Ethiopia and Serbia. At Penn State, I run actually a set of teacher workshops. In this case, the teachers are all holding up Sloan plates, but we also certainly talk quite a bit about Rubin possibilities there as well. In fact, my voice is a little weak because I was teaching this all last week. And then finally, the AGN Science Collaboration broadly also is supportive of things like the Data Science Fellowship Program. And in fact, this year, that is going to be held at Drexel University between September 11th and 15th. And I'm sure Gordon will make sure there's some good AGN science in that as well. And I'll wrap up there. Thank you.
For the talk, any questions?
Yes.
Okay, just speak up.
Just a quick question.
Sure.
So what's the smallest cadence that's technically feasible for a given magnitude?
Smallest cadence for
Like technically, like how
like where you saturate, like where you saturate on bright
no,
stars.
how fast you can sample the data.
Oh, okay, right. So the Rubin is operating, its standard mode of operation is 15-second exposures.
Okay.
Okay, so it does these 15-second, it does, or pairs of 15-second exposures, often in different bands. But in principle, it could be operated even faster. So again, if you had a truly compelling science case, it's getting a bit late to argue for this now. But I know, in fact, there has been a science case, not for AGN, but for other science, where someone is proposing to observe a particular stellar field for an entire Rubin night, continually pounding on it with 15-second exposures while cycling through the filters at various times. And so you could hammer at it with 15-second time resolution. Now, again, we are already fairly far down the path in terms of defining what the Rubin cadence will be overall. I don't think there's going to be a huge amount of time spent pounding the deep drilling fields for entire nights with 15-second resolution, but it's interesting to think about those types of science possibilities and what you could do with it.
Thank you.
Yeah. Okay.
Any other questions?
Yeah, about the deep drilling field. So some of the discussions I remember being that there could be this idea of focusing on one single field for the season. So you would do one season
Right.
Cosmos, and is that still being considered?
Yeah, okay. Can we go back? I need to go back to where we have the deep drilling fields laid out. Yeah, so part of this, a little more. I'll tell you when to stop. There we are, stop. Okay, so yeah, so part of that, of course, comes from the fact that many of the deep drilling fields lie at rather similar right ascensions, and that's somewhat inevitable because there's so much of the galaxy down in the south, okay? Cosmos, of course, is off on its own, and so Cosmos, I believe they are planning to observe Cosmos more intensively for time domain purposes, okay? That's part of it, but yeah, then because these are all crowded, my understanding, and again, this is the final way the deep drilling fields are going to be done is still being decided. But what we proposed as a science collaboration, and what I think some other science collaborations are supportive of, is to have intensive coverage of, in a given year. Say you do intensive coverage, say of the deep field south that particular year, aiming to do rapid time domain science, such as measuring the short lags associated with accretion disk reverberation mapping. And then the other fields would still have pretty good cadence, but it wouldn't be super intensive. And that allows you to accommodate doing all the observations without overloading in this given RA range, right? And then the next year you would cycle to another deep drilling field or another one or another one. And the precise details are still being decided, but that's my understanding of things. Also, and again, this gets a bit down in the weeds, but I will also mention, of course, that the Euclid Deep Field South has recently been chosen as the 5th deep drilling field. There they actually have 2 fields, so it's going to be 20 square degrees, not 10 square degrees, but they're going to be observed at half cadence, or no, they're going to each have half the amount of time spent on them, which ultimately has to mean half cadence, but exactly how they're going to phase that, I don't know. Okay. Is that answering your question?
Yeah,
Okay.
absolutely. And
that's my understanding. And if you want to know the up-to-the-minute details, I think Franz Bauer should speak to that.
All right.
Yeah.
Okay, we have time for one more quick question. Any questions online?
So far, no questions.
So one more quick question.
Hi Neil, can I just ask quickly about the membership? I mean, you said there's been a huge increase in the number of associate members, which is great.
Yes.
I'm just also aware that a lot of the names that you mentioned in the talk for people who are actually doing work are not yet full members. And so,
Oh, right. Yes. So
collaboration can maybe doing more to encourage people to apply for full membership.
Yeah, absolutely. Yes. So anyone is so here is the way that works. And I want to go back to the thing on the members. Yeah, maybe one more back. There we just do that one. Yeah, okay. So here we are. So what he's referring to, for those of you who may not know, we have a large number of members, and then there have been people who have done consistently for an extended period of time heavy lifting, when the dirty jobs have to get done, there are certain people that go and do them. As part of a reward for doing all that work, those people have been promoted to full membership over the years. We strongly encourage young people, people early in their careers, whatever, to get involved, to start doing some of that heavy lifting. And one of the rewards then is you can be promoted to full membership. Anyone, to my understanding, is welcome to propose, I wish to become a full member at any time. You can say it, and it's the same form. You just change it from associate member to full member. Now, when you do that, you have to have some justification for it. You can't just say, I have a nice smile, so make me a full member. You have to have done something, okay? And so that's how it works. So we strongly encourage people to step in, do some of that work, and this is one of the rewards that you can get. There's also another higher level called core membership, where then you have a right to be involved in some of the papers and so on. And again, you can read all the details. They are laid out in the defining documents for the science collaboration, but we want people to become full members, but you have to do the work.
I think
And
if I
some
could,
people are well on the way.
I know
to
we
doing
need to
that.
move on, but I mean, there's not really any benefit currently of being a full member. I would still encourage people to do it, but that's the reason why we haven't necessarily pushed it. The idea was that if we had money, you would need to be a full member to get the money, and we just don't have any money. But core member is supposed to have publication rights, and so, people should be encouraged to apply for full membership if they've been active.
Perhaps we should modify or think about modifying the process, because it seems like it's not really working.
Well, how about since we have to move on, why don't we have these discussion sections?
Yeah,
we
we have
can
discussion
chat about
sections.
this more in
We
discussion
can
section,
leave
or
the discussion
offline,
later.
however you
Yeah.
want. Yeah.
Let's thank Neil again. So our next speaker will be Neven Caplar. We will talk about LINCC, developing software for large-scale analysis of data.
Ilsang, would you write up the Slack
Yeah.
channel?
I'll do it.
Yeah, so just a reminder, our talks are 25 plus 5, including 25 minutes of talk and 5 minutes of questions. And yeah, I will do a reminder like several minutes, I guess 3 minutes before end of the talk. Okay.
Okay, so yeah, thank you. So my name is Neven Caplar. I'm half-time involved in LSST commissioning, but today I'll talk about the other half of my time, which is working on LINCC frameworks, which is where we make low pixel images.
Let's try one more time.
Okay. So what is LINCC frameworks? So LINCC frameworks is if you go to the next line, it's a collaboration between University of Washington, Carnegie Mellon University, LSST Corporation, University of Pittsburgh, and National Optical Infrared Astronomy Laboratory to build software systems for the key LSST science. It's a project funded by Schmidt Foundation, which is a philanthropic foundation funded by Eric Schmidt, who was a Google head person for a while, and Andy Connolly in Seattle and Richard Manbel in Pittsburgh are the key PIs, and this is our group. And the goal is to create science software infrastructure. So combining user algorithms and code and all the astronomical packages with the industry tool, with the software engineers to help us make it scalable to the level that LSST science will demand. So if we go to the next slide, I will just a little bit elaborate on that point. So what do I mean by that? So our mission is to enable scientists to develop and productionize these software algorithms, and to do that in collaboration with broader community. The goal is, when you have LSST data management team, they will spend a lot of time and effort to create these wonderful products where theoretically you get the perfect data products at the end. And our goal is to enable scientists to take these vast amounts of data and be able to generate science from that. So our goals are to be engineering and algorithmically focused, to collaborate with other software efforts, for instance, AstroPy, and I will show you an example later, to leverage existing tools, for instance, Rubin Science Platform to be number one, and then coordinate with community to avoid unnecessary duplication of effort, especially with in-kind contributors, in order to not trample or, you know, like overtake other code that other people have already done. It's to improve such efforts, but not to trample them. Exactly. So there are multiple avenues in which we are doing this collaboration. So there is like software component that I will talk later, but there are some others as well. So there are workshops. One of them was in March 2022, which was created a white paper, which basically puts forward what we are doing, what we want to do. There'll be other workshops in the future. Then there will be incubators. I will talk a little bit more about that because what they allow us to, you apply, we give you access to some money and software engineers to improve your effort. And then the tech talks, which I will, because I had them, there will be a lot of advertising as well. But basically they are to showcase the software effort done in the broad Rubin community and activities. And then, as Niel was mentioned before, having members in LSST science collaboration, which in this case will be. Okay, so I'll talk about incubators a little bit. So as I said, they provide software for researchers to work directly with the LINCC framework team. So the software engineers, so people who came from mostly, it's, you know, Google, Amazon, people who don't really know astronomy, but have very good computer science background, and help you apply your science on the scale of LSST. And in longer term, to create collaboration where we, in the years to come, can collaborate and make sure that your software is working on the scale that it should. There have been already 2 proposals which already gone out. One was finished a month ago, and it will be announced the selected proposals in mid-August. Just for reference, for instance, in this round, there were 9 proposals, and then we have several layers. There's a second stage, which 5 got selected in this round, where we basically talk with you what are, you know, like a little bit deeper investigation. What do you want to do? What are the possibilities? And then in each 4 months, we select 2 incubators to work for 3 months, and it's around 25K that you get. So the next proposal deadline is October 15. It's not announced yet, but the expectation is that they will come every 4 months. The good proposal, personal opinion. Okay, so this is like what I see as good proposals, and I think these will be soon a little bit more elaborated in written form. But basically, the main one is you want to have proposal which aligns with the work that we are already doing. And this is just simply, even though it's not a small group, it's around 10, 11 software engineers, and then there are 5, 6 project scientists. There's obviously a limited amount of work that we can do. So if it already aligns with something we are doing, that's obviously helpful. And I will go through what we are doing, so that will maybe help you as well. The second one is scales existing proof of concept or scientific code. And this goes a little bit to what I was saying before. Software engineers are great, but they really don't know astronomy. I mean, you know, it's like undergrads in a way, you know, even worse. So you need to have, you can't expect them to solve your science problems. You need to have something which basically already works, and then we can help you scale it up, okay? So the basic scientific code needs to already be there, and I will show you some examples even later, but even now. So just for example, yeah, please. So for instance, the first 2 incubators which were selected were solar system simulations. So this is an effort by spearheaded by Universidad Belfast. So it is, as you know, there are these data previews. Data previews 1, data preview 2 for LSST, and then there will be data preview 3. And the difference from 2 is that it will include solar system objects. And so maybe that was relevant for this group, but you see what they are doing, they already had a simulation and they're just basically scaling it up to be much faster, because now they did it like once and they barely did it. They want to be able to make these simulations on the fly, basically in the future. And the second incubator is from the Penn State, and it's a supernova classification proposal where, again, they want to be able to, you know, all the machine learning, what they are doing, they just want to be making faster for larger amounts of data. Okay, the other thing that we are working on are tech talks, which happen second Thursday of every month, 10th AM Pacific, and we have been advertising those as well, as you know, and I'm very grateful for many of you who have attended. And there were some talks which we already also got from, for instance, Serbian AGN group, which were presented there. We talk about science, but with a larger technical underpinning. So we are interested in software that you're developing. What were the challenges that you had? So far, we had talks from brokers, from NRAO contributors, data centers, our own LINCC framework software engineers. In the future, for instance, one of the things we will continue with those, but also more results from the incubators and talks from the Roman software group, which they are also scaling up. Okay, so I want to talk about some of the projects that we are working on. There are 4 pillars going together. So one of them is KB mode, and it's stacking images, and so it's a way to detect solar system objects without stacking images. But again, because there are no AGNs expected in the solar system, I won't talk about those. The second project is this one. It's called Rail, and it's for establishing photoses, and some of you might be familiar with that. It's a toolkit to build pipelines to estimate and stress test photosy products. So basically, the main idea of that package is to be able to compare various photosy algorithms. So it's quite modular. So there is like a part where you create mock data, and then you can put it through the photosy algorithms. And you see there are many, I of course know there are many words here. I know none of these codes, but you can test many of these codes. And then there is another step where basically you can create metrics in order to estimate how different algorithms are performing in different regimes. And it is the code which is adopted by the photosy commission team. Okay, so we'll come to this slide couple of times. I wanted to tell you more about the time domain effort, which is what is my background, and I will talk the most in this talk, and what we are doing from that side in LINCC. So there are a couple of efforts. So one of them is AstroPy contributions, and then there's a dedicated time series analysis and basically cross-matching analysis part. So let's go talk about AstroPy a little bit. So if we go to the next slide, one thing which we made a contribution to the AstroPy is this one. So basically multi-band periodograms. So we took a code which was in the package called Gatsby, and which was already mostly ported to AstroPy, but the part which wasn't ported was of course the most difficult part, which is a code from this paper from 2015, which enables you to generate multi-band periodograms. So basically you fit multi-band light curve, you assume that the phase is the same, but amplitude can differ. And you can recognize the AstroPy help pages where, you know, it's not very clear, but you can fit such a phased curve. The problem with AstroPy code is, so for instance, I will test your eyesight here, but basically, so it's submitted November 16, 73 comments, merged April 19. So, you know, to merge something with AstroPy, especially time domain, it just takes a lot of time, because that project is also a little bit underfunded. And also, you know, you need to jump through many hoops and many tests in order to make sure that you're compatible with the rest of the AstroPy. So that's in. I encourage you to use it. The problem with this code, just to, you know, for warning, it's not fast. it's not something that you will be able to apply on the LSST scale. It works very well, but hundreds, thousands light curves, not millions. So if we go back here, yes, please. So other efforts that we're doing, one of the things is we are developing is this module which we're calling TAPE, time series analysis and processing engine. And of course, we have grand plans for it. And here in the sub points, I just will talk about things that we are developing at the moment. In longer terms, what we want, we got a lot of inspiration from the package called LightCurve. So LightCurve is a package for working with the TAS and Caplar data. And what is amazing about it, if you go to their website, it's so easy to use. You can load in LightCurve in a second and work with the data. If you want to take LightCurve from data preview, if you go to the data preview notebooks, if you want to get a LightCurve now from the data previews, there will be 7, 8 cells of the code which you kind of need to work, and a lot of intrinsic knowledge. So in long term, that's something that we want to enable, that you can get LSST data easily. So LSST data is coming, but it's not imminent. So we are working on making sure that we are able to scale up codes with the precursor data, imagining how this will work on the LSST scales. So one is the scaling of external functions we have asked. I will talk about that. Some is writing internal functions, maybe periodograms, structure functions, which I will describe. Some functionality which will be useful for community. At the end, I will talk a little bit, if we have time, about aggregating broker results. But first, I want to talk about this other package, which is closely related, which is LSDB, which is cross-matching package. So if we go to the next slide, it's a package developed by these two individuals, Samuel Wyatt, who is a project scientist as well, and then Mario Juric, who is faculty at University of Washington. So I took these slides verbatim from them. Basically, what they're saying is, as you kind of know already, it's all the same riff. This will be a huge data set. You want to be able to cross-match with the previous data sets. This will be very large, so basically it will be much more difficult to cross-match than it was ever before. You can already see that if you're using Rubin Science Platform. So they are developing a package which will be able to create such large-scale analytics and cross-matching, okay? The basic below it is the HipScat. So if we go to the next slide, please. So it's a hierarchical data storage scheme. What does that mean? Basically, they took, if you look, this is Gaia data set. You want to separate that you have many files, the whole data set of the sky is separated in many files, and that each part of the sky that you have is not same part of the sky, the same file has same number of rows. And what will that allow you to do is many things, but basically I will show you an example where you can, how this will help with cross-matching. And then all of these files will be stored as Parquet files, which is like Apache Parquet, relatively fast data format. So if we go to the next slide, what you do is in the parts of the sky where you have many objects, you just keep chunking until you have that each folder, each file has same amount of files. So you see in the areas where there are many object stars, most likely, this is Gaia, you will get to the order 7, so order 1, 2, 3. So, and this is all in these folders. And depending when you want to find an object, its position on the sky, you don't have to load the entire catalog. You only have to load that one particular file that you want. Okay, so if we go next, so can we go back just for a second? I really wanted to point out this link here. So they have a wonderful presentation, like a 20-minute presentation, which explains this to much greater detail. And there will be presentation also at Project Community Workshop and at ADAS, which is a astronomy software conference in Tucson in November. Well, they will have a 1.5-hour tutorial. So I really encourage you to do that. But basically, this is showing you how this cross-matching works. Let's say you have these two catalogs that are split in this kind of object. you can very efficiently cross-match them because each of these cores can load each pixel in the memory, and then you are cross-matching them in each individual core and not overloading the memory. So like if you have sufficient amount of cores, basically you are working as if you loaded everything in one go. Okay, so this is somewhat aspirational, but this is how Mario envisions how this package would work. So that you will have, you will write these analysis lists where you will take, for instance, Gaia catalog. You will do a query, everything that has proper motion larger than 10 arc seconds. You will cross match it, ZTF sources. So you will then get the light curves. So I will talk a little bit, so how in LSST you have object and sources, meaning basically time domain data, classify, query, output the data for. And basically be able to run that on Rubin Science platform or your own Google Cloud, basically behind Rubin Science platform on your local cluster machine. So at the moment, it's working on Dask, which is again software tool to do parallel computation. This is a little bit old slide. May look at Ray. I think we are switching to Ray, which is again just a different Python parallel scripting language. Dask has a thank you. That's good. Ray Dask has a good thing that is supported by LSST and Rubin Science platform. So then I wanted to talk a little bit about TAPE, which is this time domain project that we are developing. As I said, built on top of Dask, parallelized Python packages. The how we see it is that you have your time domain data coming from LSST, ZTF, Penn stars, from your output, which you did from a cross match. You can load it and process it and apply your function. So you supply your user-defined function, and hopefully it just scales up relatively simply. So if you want to parallelize relatively quickly, we are working that basically you don't have to think about it at all. And then there will be some other analysis functions which we are developing either for our use or for use of the community or basically other LINCC fellows. And I will talk a little bit about that. But if you go to the next slide, so this is how it works at the moment. Basically, you load your object. So this is from Penn stars. And then you have objects and sources, which mimics how the LSST database will look. That you have objects, which are basically co-added images, things that you find on co-added images, and then sources basically means that actions. So if you have a time domain, it will all be in sources. And then you could note here that it says compute. Why do I have to do compute? Because Dask does this thing where it's like lazy loading. So if you want to have a large computation, you are not actually loading everything in memory. You are distributing this to the workers and then operating on the workers. So if you want to see the data, basically you want to do this compute to show it to you. And then you can do things like, this is such a silly example, but removing everything which has less than 100 observations, and then doing functions such as structure function, and you get the result here. This is just a slide which I like to show because it's very nice and has an impression that we know what we're doing. I will talk a little bit about some of the scientific aspects, some of the scientific functions that we have. So if you go to the next slide. So one of the things which we are developing is structure function, because so often you see things like that, right? The main analysis routines were written in IDL and are available on request. And so we want to rectify this, especially structure function, as you maybe know, it's like an axis variance calculation. It's relatively simple function, and it's simple, so people just keep rewriting it. So we wanted to basically solve that problem. If you go to the next slide, we implemented this. So basically, it's faster, and we put all bells and whistles inside, and also it helps us in order to test how quickly we can analyze all of this data. And here I have an example of working that on an ensemble of many light curves. I wanted to show it with error bars, but then the code crashed. So, it's still work in progress. So if we go to the next slide, one of the things also which we are working on is, this is a project by Penn, who is also a LINCC fellow, soon to be faculty, is the periodic detection. So for instance, we have LSST data, and this is basically simulated Jupiter, something that TESS is very good at observing. And if you have 10 years of data, as you can see, this is very easy to see. But of course, this is only after 10 years, and it will be very rare. So basically, you want to find these drops very quickly. And if you go to the next slide, when you phase fold, this will look great, but the LSST has different challenges than TESS. There will be many more light curves. They'll be much sparser. So you want to develop this detection algorithm, which will be very different than TESS. And particularly, it has to be faster. And you want to do that. You probably want to do some sort of multiple layers of finding these drops. Okay, so maybe let's just skip this one. What I wanted to talk is this slide. I have been very interested in exploring JAX. So JAX is the library by Google, which enables you to do just-in-time compilation, auto-read, all the fancy words from machine learning, differentiate, all of these cool things. And there was for instance, plenary talk by Dan from Mackie at AAS conference in January. And it enables you to do very fast Gaussian process estimation. So on the right-hand side, there are many curves, but what I'm doing is what I think Maria Carisi will also talk about tomorrow, is where I'm trying to fit a light curve with both periodic oscillations and damped random walk. And, many curves, but, it works. That's the point. And if you go to the right-hand, next one. Yeah, please. So Dan has, why do you want to do it? Dan has this slide where you are doing a benchmarking. So this is celerity, which is the previous state-of-the-art code, which is basically there's a C below. But you can see that if you write this code with this JAX code, you can get performance like 10 times faster, again, depending on number of your data points. There are many caveats here. Basically here, for instance, I'm writing some of them. There's a compilation cost. And if you go to the next one, this is the slide which I did yesterday. And this is the last slide. So for instance, this is the celerity code, and this is the TinyGP code on CPU. So you can see that you can get maybe 5 to 6 times faster compilation. This is GPU estimates. So you see GPU, depending how there are many this like which optimizer I'm using and such, but you can see with GPU, there's like initial time, and then later you are able to basically match CPU performance, but not in this case, you're basically the same. So let's basically skip this one, and I think I will end with this. Thank you.
Any questions?
I'm glad that I'm here to hear your talk. We need to talk offline more, but I am developing time series analysis tools also, and for LSST, I think it's better if we have a bigger platform which can run many sources in parallel.
If we can have, sorry?
If we can run like many sources, it can handle reduced data, and it can handle both evenly sampled and unevenly sampled data.
Right. And multiband, for instance, I think.
Yeah,
exactly.
So I'm also I'm also looking for somebody who can help me in setting those platforms ready before the data came in.
Right, and I think so. Maybe I want to emphasize that a little bit. For instance, what make that a light curve package for tests so useful is that it's specific to light curve. And why nobody uses AstroPy time series is because it's so general that you are basically, the package is so general that you don't have actually any functionality in it. So there is some interplay in between where basically you want it to be LSST specific enough that you are actually getting some benefit from using it. And I think what makes LSST specific is multiband data, heterogeneous data, and large scale. And that's what we're trying to aim at. Yes, let's talk more.
Any other questions?
So
Back to back,
regarding
yeah.
and regarding the
Yes.
special function package, is that providing also error bars for the mission?
So it should provide error bars. And then when I was trying to make a plot, it crashed. So, and this is, again, working with software engineers is very interesting, but the problem is, they write it, I write like design document, they write it, they write unit tests, then I try to apply it on real data. Often it doesn't work. So yes, definitely should provide errors via bootstrapping, right? That's how it's written.
And how fast is?
It's not fast at the moment, but definitely it should, that's something that we can work on. The initial implementation at the moment, unfortunately, I think I did 100 light curves with 200 data points. It took me still a minute, which is unacceptable because I want to apply that on millions. But that's initial implementation, but I think we can really do much, much better. Because once when it works, I can kind of dump it and say, make it faster. We are really good. We are very good at that.
Okay, I think we have an online question.
Yeah, so Eric, can you unmute yourself and ask a question?
Sure, thanks. So you mentioned testing of various codes on periodic signals, and I'm wondering about whether there has been any testing on quasi-periodic signals, which are both tougher to find and also tougher to deal with.
In the JAX example, for instance?
Sure.
This last thing that I was talking about. I will assume that that's a yes to my question. So quasi-periodic signals should be the same, just more difficult because you have more parameters. So I presume it will be the same, but we haven't gotten there yet. And I think there are some problems when it gets a little bit more complicated, but theoretically the speed up should be the same as when compared to Celerite when you're using JAX. I'm not sure that's the answer to the question, but.
Okay. It's enough, thanks.
Okay, thank you so much, thank you.
Yeah, I think we are out of time, so thanks, Neven, again. So we will have a coffee break from now and between now and 11. So if there's more questions, we can discuss in the coffee break. And yeah, see you at 11. So this is the second half of our morning session. So our next speaker is Paula Sanchez Saez. She will talk about searching for different AGN populations in massive data sets with machine learning. And please take it away.
Thanks. So hello everyone. So today we'll tell you how we are using machine learning within the LSST broker to search for massive AGN populations. Let's see if this works. Okay, so I'm sure I don't need to give you any context about AGNs, but just to remind you that AGNs are variable and they show variability that is described as a stochastic process. And the level of autocorrelation within this stochastic process defines the time scale of the variability. And this time scale varies between a few hours to several years. So normally when we obtain, yes, you can see this, right? Yes, when we obtain the power spectral density of an AGN Lycra, we obtain something like this, that is a bending power law, and the time scale is this bending time scale. And also, these properties in the AGN Lycras are also correlated with physical properties from these sources. We know from previous works that there is a correlation between the time scale and the platform mass, but in recent works, we're also finding that there is a correlation with the time scale and the accretion rate. So it's a mix of platform mass and accretion rate. And this is a series of papers that has been submitted recently, led by Patricia Arevalo. And we also know that the amplitude of the variability is anti-correlated with the accretion rate. So we can use variability-based selection to identify very broad populations of AGNs, but in particular, this kind of selection is very efficient in finding low mass AGNs and low accretion rate AGNs. And then also during this talk, I will cover a selection technique to identify changing look AGNs. So in case you're not familiar with them, these are sources that change their classification as type 1 or type 2. And normally when we see this transition, we also see a large change in the optical flux. So we can use optical variability to select candidates of changing look AGNs. So in this talk, I will cover these two topics. First, I will tell you about a very recent work where we are using CTF data releases to identify AGN candidates, and then an anomaly detector to search for changing look AGNs. So first, the variability selection. So again, we are using the variability, and the idea is to cover the very low end in terms of black hole mass and accretion rate, in particular for the changes survey, which is one of the community surveys for the foremost instrument. And for this, we're using the Zwicky transient facility. So I guess you're familiar with this. So this is a survey that's been conducted since 2018. And it's very efficient for time domain studies because we have more or less observations every 2 or 3 days in the D and the R band in the public survey and the I band in the private survey. And the magnitude limit is around 20.5, so it's very efficient for AGN studies. But if you want to search for broad populations of AGNs, you have to move out of the alert stream, because the alert stream, which is the data that most of the people use, is very biased towards the most variable objects. But if you want to search also for more massive objects or high accretion rate objects, you need to go to the data releases, which contain the whole information, not only the most variable objects. The problem with the data releases is that it's PSF photometry over the images. So all the images are used in this case, but it's PSF photometry. The problem with this is that for extended objects, you will have just noise. And you can see here an example. This is a known passive galaxy for which you have this Likert, which is super noisy. And it's just related to variations in the seeing conditions or the weather conditions. This is the same for a non-variable star, and you see a much flatter Likert. And then here you have an AGN, quite variables AGN, and then a transient, where the transient is almost detected. You can see something here, but it's very noisy. And then an eclipsing binary. So if you want to classify this data set, you need to have proper features to remove the problems in the data just related to the extension of the source. So for this, we're using this hierarchical tree to define our taxonomy. So since we have Likerts that are non-variable, but in some cases we have point sources, sometimes we have extended subsources, we are using this first level where we separate sources as non-variable stars, so point sources, and non-variable galaxies, extended objects. And then we have the variable class that includes everything, so transients, stochastic, and periodic sources. So we're using this very broad taxonomy tree because the idea is to not only focus on AGN science, but also to provide candidates for transients and periodic variable stars. And for the case of stochastic, we have 4 classes of AGNs, and we are separating first AGNs in terms of redshift. So we have 3 redshift bins: low redshift below 0.5, mid redshift between 0.5 and 3, and then high redshift over 3. And also we have places for the very rapid variations where you have a jet. And then also in this class, we have YSOs, young star objects, and it's important to include them because normally they are misidentified as AGNs if you don't pay attention. And I will show you later a few examples where we have found YSOs in AGN catalogs. So since this is a hierarchical taxonomy, we are using a hierarchical approach to classify. I don't know what's, I can see the picture, okay, yeah. So we are using this hierarchical approach where we basically have one classifier per node. So this is called local per parent node hierarchical approach. And in the first level, we have a classifier here that separates variables, non-variables, and non-variable stars. And then we have additional classifiers on each of these nodes. And then since we are training with the known objects in the literature, we have a problem of imbalance. So you can see here, this is the training set we are using. So we are constructing this training set by combining all the known sources from the literature for the different classes. And then we cross-match that with the CTF data. And we have many mid-redshift AGNs and also non-variable stars and galaxies, but we don't have many C-fates or supernovae. So how you can deal with that is by using this very nice balanced random forest. That is a very simple way to deal with imbalanced data sets. So what it basically is doing is every tree in the random forest will see a balanced version of the training set, but at the end, the whole training set will be visible for the full random forest. So in that way, you don't have to do data augmentation, you just use the imbalanced random forest. And also since CTF for the data releases is not providing unique identifiers for unique objects, you have a unique identifier for a unique combination of band, field, CCD, and quartile. You cannot have a multi-band classifier. So we are using single band. And this is because mostly it's super expensive to cross-match these different bands, because the number of points, sorry, the number of sources in the data lists are huge, billions of objects. So combining them is very expensive. So we decided to use a single band approach. So since we have all these problems in the data, we need to have proper features. And for this, we first computed some colors from additional catalogs. We are not combining CTF Likert, so we take the colors from other data sets like Catwise and Pan-stars. And we also have a morphology score from Pan-stars that is very convenient to say, okay, the source is extended or is a point source. And then we have an addition of 61 single band features computed from the CTF data list Likert. And among these features, the most relevant for AGN classification is this Mexican hat power spectrum that I really want to highlight because I think the community is not aware of this feature and is not using it a lot, but it's one of the main features we have in LSST. So it's basically a way to compute a low resolution power spectrum. So you can see here an example. This is an X-ray Likert with a very rapid variation, short time scales and also long time scales. And what we do here is convolve these Likerts with a Mexican hat filter that has a width that is the time scale that you are trying to isolate. So you select different time scales and then you convolve the Likerts and you get things like this, where you have the very short variations, rapid variations, and the long-term variations. And then you measure the variance for each of these Likerts and you get this low resolution power spectrum. That's super efficient and quick. It's much quicker than doing Fourier transfer analysis. And in the case of this classifier, we selected 2 time scales, so 10 days and 100 days. And we measure the variance at these 2 time scales, and then we measure the ratio between them to have an idea of the slope of this power spectrum. Why we are using those time scales? Because they are very efficient to separate AGNs from other variable objects like YSOs and long period variables, which can be contaminants for the selection of AGNs. And also we have the other 61 features. And here I want to show you a comparison of how you see in the data list Likert this feature distribution for non-variable stars in blue, non-variable galaxies in red, and AGNs in pink. And you can see if you use traditional features like the excess variance, AGNs and galaxies look very similar. This is because the Likerts are just dominated by the noise. But then if you use more complex features like this regular autoregression function that measures the level of autocorrelation within a Likert, you will see that AGNs tend to have values close to 1, so very autocorrelated, while galaxies and stars can have values close to 1, but also close to 0, so no correlation. And this is because the these are just dominated by noise. Then you can use also, for instance, the time scale, and this is also very traditional in the community. From a time random walk model, AGNs will have time scales that are closer to 100 days, which is expected from the black hole masses. And then galaxies and stars will have a time scale that is close to the cadence of the layers. And then here you can see the distribution of the Mexican hat features. So if you want to separate stars, galaxies, and AGNs, you need to compute also the ratio, because in the ratio you will see the difference. That is the slope of the forward spectrum. So with the combination of all these features, you can do the magic and select AGNs, even if you have very noisy layers. So you can see here the confusion matrix we're obtaining for the D band. In the case of the air band, the results are very similar. And you can see that it's quite diagonal. The problem is we're missing some of the low redshift AGNs, as you can see here. And also the transients are confused with non-variable galaxies. But this is expected because for the case of low redshift AGNs, if you have faint sources or low luminosity AGNs, you won't be able to distinguish the variations from the noise. So you will miss a fraction of them as non-variable galaxies. And for the case of the transients, the photometry of the data analysis is over the center of the galaxy, not the transient. So you miss the transient if the source is very far from the nucleus. So that's why we have this fraction of transients as non-variable galaxies. You can see the same here for the YSOs, which are also stochastic, but are confused with point sources. And here you can see what we obtain when we classify all the sources in the data list that are in the south sky. Because the idea is to find objects for changes. So changes is in the south, so it's a foremost survey. So the idea was to search for all the candidates in the overlap region between CTF and foremost. So we classify more than 86 million objects in the T band and more than 140 in the air band. Now, if the community is very interested, we will apply this to the whole data list, which is very expensive because it includes several billions of objects, but we can do that if there is a lot of pressure from the community. And you can see here the number of candidates per class. We found this problem where we have a very normal fraction of high redshift AGNs predicted in the T band, but in the air band, you see this crazy number. And this is super important for this community because the problem is related to the cadence of the light. So we found that after checking the problems in the features, there are some regions in the air band, in the CTF sky that are highly observed with an extremely large cadence. So you have sometimes 200 observations in one night. And that totally skews the distribution of the features. So if we use a generic model that contains objects with a few tens of epochs and then thousands of epochs, of course, the feature distribution is going to be a problem. So from this, what we can suggest for LSST studies is that you can have models that works in the deep brilliant fields and others in the white fields, so to avoid this kind of problems. But at the moment, for the changes collaboration, we are just using the G-band features, and then only the high probability candidates in the R-band are included. And this is a comparison of our results with previous works. So this one, 10-2020, was using data list 2 to classify only periodic variable stars. And you can see here that there is a good agreement between the classifications, except for the classes that are not included in our taxonomy tree. And we have more classes, so we have also transients and AGNs. And we found that a few of the periodic variable stars were classified as AGNs or other classes. And then we have here a comparison of the data list classification with the classification that we do in ALERCE using the alert stream. And you can see that it's also very in agreement, but there are some sources that we miss as non-variables. And this is just because we don't have the same data. The alert streams are centered in the alert, while the data release is centered in the center of the object. So if the supernova is very far from the center, you don't see the supernova. So that's regarding the classification we are using with traditional machine learning techniques. But now I would like to tell you about this work where we use anomaly detection and deep learning to find changing look AGNs. So again, just a reminder, changing looks are these sources that change their classification as type 1 or type 2. And recently in this paper by Superlak 2021, they propose that these sources are outliers when you see the distribution of that random walk features. So after we saw this paper, we say, okay, why don't we try anomaly detection to find changing look AGN candidates? And we have a model that is now running with CTF data, but it can be easily applied to LSST. So just to let you know what is anomaly detection. So it's this field within the machine learning field that is able to find rare objects within massive data sets. And these rare objects can be intrinsically rare objects within a distribution of properties like this, where you have intrinsically very different objects respect to the normal population. But also you can have contextual anomaly where there is a source that was normal and after a while it's not normal. Like this example here, a periodic signal that is flat and then it's normal again. And for this, we can use contextual anomaly detection. A particular tool that is super efficient in applying these both approaches is variational autoencoders. So in case you're not familiar with them, these are a modification of the more classical autoencoders where you have an input data set. It can be images, time series, or a table. And then you input this data into an encoder that compresses information into a latent space. And then that latent space is used to reconstruct the data. So you get a compression and a decompression of the data. And the main difference between autoencoders and variational autoencoders is that the latter has a variational distribution in the latent space. So you have, instead of one single vector of values, you have a probability distribution with this that is described as the mean and the variance. So if you have a probability distribution, then you can generate new latent space for each. I don't know, if you want to reconstruct 10 images or time series, you generate 10 versions of the latent space, just perturbating the latent space around the average and the variance. And then you can have several versions of the reconstruction. So you can use this as a generative model. The advantage of doing this is that you will group together in the same region of the latent space sources that are similar. Because the idea is that if you only perturbate a little bit the latent space, you will get a similar reconstruction. So this is super efficient for anomaly detection because this means you will have objects that are similar in a similar region of the latent space and sources that are very different in another region. So how you can do anomaly detection with this? First, you can take the latent space as a set of attributes. And this has been done a lot in the astronomical literature. For instance, in this case by Ashley Villar and collaborators, where they use the latent space as a set of attributes with isolation forest to identify anomalous light curves of supernovae. But then you can also use the reconstruction error as an anomaly score. Because whenever you reconstruct a light curve, you can compare that reconstruction with the real data. And if that difference is large, that means probably the source is an anomaly. For instance, in this case, we have a periodic signal. If we train a model that is able to predict periodic signals, and then you apply this model to something like this will be probably not reconstructed properly. So you can use this difference in the reconstruction as an anomaly score. And that's what we are doing now. So for the case of AGNs, we selected all the known AGNs with data in the CTF data release 5. And we applied this model, but we use the blazars as a control sample because the idea was to say, okay, if we train a model only with AGNs, which are intrinsically different from blazars, do I identify the blazars as anomalies? So then I can test if I'm able to identify variability that is similar, but it's not exactly the same. So we use this, we were inspired by this work. They were using autoencoders and we only included the variational part. So that's the only modification we have in this architecture. But we also trained the model using a balanced version of the data. Why? Because the idea is to do anomaly detection. And if you train a model that is dominated by very bright or massive sources, then you will identify the less luminous or less massive sources as anomalies just because they are not super represented in the data. So the idea was to train with a balanced sample in terms of physical properties. And then we applied this to the whole data set. And also we normalized in terms of the number of epochs per source, because the idea was also to avoid classifying the sources with more points in the Likert as anomalies, just because they are not allowed in the city of data. So then, after training, we apply the model to all the AGN sources in DataLS5. And here you can see the results when we use the reconstruction error as an anomaly score. So all the sources with more than a reconstruction error larger than 3 were selected as anomalies. And then for the sources with a lower reconstruction error, we use isolation forest with the latent space and selected the 2% more outliers, like anomalous sources. So after this, we obtained a sample of almost 9,000 anomalies. Most of the blazars were classified as anomalous, so this is good. We are classifying intrinsically different variability as anomaly. But then when we checked all the candidates that were normal AGNs, we found problems in the photometry, like examples there. So these are problems in the city of data that are not easily identified using the flags. So if you use the flags that are normally provided by the CTF collaboration, those images are classified as good images. And of course, there are problems in the data there. So I will say that 90% of the sources were problems in the data. And then we also find problems in the parent catalogs. So we found several YSOs and CVs in the AGN catalogs. So please, this is important. Maybe if you use this Milliquas catalog for your science, take into account that there are a few YSOs and CVs. So then we selected, after removing all these problems, we selected 75 candidates that were showing flaring activity or an abrupt increment or decrement in the luminosity. And we are now in the process of confirming the nature. So we had, thanks to Matthew Graham and collaborators, we have access to telescope time in Palomar to confirm the nature of the sources. We are now processing that data. And also, we have been comparing their candidates with our candidates. It's a work that is not publicly available yet. It's in preparation. But we know that 28 of our candidates are in common with their candidates, and also 4 of them are already confirmed in the previous work that was published in 2020. And also 2 of them are also confirmed in a work that they are preparing. So you can see here some examples of the candidates. So yeah, that's the summary. So we're using machine learning to find very broad populations. So first, we're using more traditional approaches to search very broad populations in terms of physical properties. And then we're using deep learning to identify changing relations.
Any questions?
Hi, thanks for the talk. I was wondering about the probabilistic approach to classification, because here you're showing this kind of binary, is it AGN, yes, no, is it supernova, yes, no, and the confusion matrix kind of reflects that it either is or isn't. But you, on slide 21, showed this illustration of latent space where you have a probability distribution, your sample is somewhere from that distribution, and I wonder if you consider that for your broker, for instance, so that you could use Bayesian, methods. You could use MCMC, some sort of posterior, where you really have a distribution of your likelihood of your label, really.
Yeah.
So you know what I mean.
Yes. So the first part of the answer will be, okay, we have probabilities. So with this hierarchical random forest, for each label, for each node, we have a probability. Of course, you can play with those probabilities and do your own cuts. So we are providing the probability of each classifier, so you can do cuts there. For the case of LRC, also in the Likert classifier, we have a slightly different approach where we multiply the probabilities to avoid problems in the first level. So if, for instance, the source is non-variable, but is classified as variable, then if you propagate the source in the other nodes, you will get very low probability. So you can also use that to resolve problems in the first levels. That's for the alert classification. We're not doing that here because it's very expensive. So we prefer to use very simple strategies to deal with billions of objects. If you use more probabilistic approaches, that is okay with a few 100,000 of objects, but if you deal with billions, it's probably not the best if you want a quick answer. So that's why we're using this very simple approach. Of course, we can then, once we have this set of candidates, we can do a refinement of the classification with a more probabilistic approach, but that's only possible for a small subset. So that's why the simple answer is we have too many objects to deal with. So that's super expensive.
Any other questions?
So what code are you using for your balancing of the training sets, and would it scale to something 10 times larger?
For this part or the other?
For both, really.
Okay, so here is very simple because the random forest implementation of the imbalance learn package is one line of code. Is you call it very similarly like when you use scikit-learn, it's the same interface. So just replace, instead of normal random forest, use imbalance random forest. For the other part of the work is basically a grid where we take the set of properties and we create the bins in terms of physical properties, and we selected randomly the same number of objects per bin. So that's more like a more manual way of that.
Any other questions?
I think Neil was first.
Okay, then you.
I don't mind. Okay. So have you been able ever to take all of your work with ZTF and scale it to Rubin to make forecasts as to how many change in the quasars you expect per year, how many other anomalous AGN variability events you expect per year, or even connecting up with Dimitra, who's worked on this from a different way, just how many AGN you expect to be able to select from variability overall?
Yeah, I think not yet, because we are still refining the problem is the photometry. So it's hard to scale CTF to LSST because the quality of CTF data is very low compared to what we would have with LSST.
Mm-hmm.
Now we are doing our own photometry. So we are taking all the CTF images and conducting aperture photometry. I think after that, we will be able to do predictions, because now I'm sure we are missing many sources just because the Likers are super nice. So after that, yeah, we definitely will do that kind of analysis.
And do you think you're going to be able to, for example, to jump on change in look AGNs very quickly with Rubin, given the way the data will be distributed, where they're going to have these big annual data releases, and then there'll be alert brokers providing things when you have enough to get it all out?
Yeah, actually, the idea that we have now is the method we have already is okay if you are dealing with data releases, but to deal with the alerts, you need something more that works in real time.
Yeah.
And that's something I'm working on right now. I cannot show you results.
That's fine. Okay.
It's something we're planning, because the idea is to predict the behavior of the sources in real time and then alert the community when there is something changing definitely from the prediction.
Absolutely. Okay.
Okay, thank you. I think we are out of time. So thanks, Paula, again. Gordon's gonna talk about a kitchen sink machine learning approach to LSST AGN selection.
Okay, great. So I'm going to talk about work that we're doing at Drexel, and I want to thank Georgia Savage, Ashkarale, who's here with me, Wei-Zhang Yu, who just graduated, Franz Bauer, who I've stolen some slides from, and so on. A lot of this is going to be similar to what Paula has said, but more theoretical. Like, this is stuff that we want to do when we actually have money and time that other people are already doing, and so including Paula and Georgia. So it'd be nice to talk to people and get together and work together on these things. So first, start with some expectations. LSST by itself should identify something like 10 to 30 million quasars and AGNs, just using data that's internal to LSST. But we expect to detect something like 300 million AGNs, and something like 10 times the number we're going to select by itself, and maybe 1 to 2% of all detected galaxies. And so we have to deal with obscuration and host galaxy contamination that is making it hard for us to identify those 300 million objects as AGNs. And the hope is that when we combine with multi-wavelength observations, we should be able to then recover, maybe 100 million of those or something of that sort. So I want to spend most of the time talking about problems that we need to solve in this. I'm going to go through 4 different things. One is just sort of different types of AGNs. The other is, how you make use of all of the data, like literally all of it. The fact that our training sets are unrepresentative and relatively small. And then the fact that we have sparse and missing data, and we need things to scale up to 40 billion objects. And so I'll go through each of those separately. Okay, so AGNs are in a way a monolithic class of objects. They are galaxies that have a black hole that's actively accreting new material, but they present in a very non-monolithic way. So we've got type 1 versus type 2 versus low luminosity versus high Z, where what I mean is we have things that are dominated by the continuum from the accretion disk, things where that continuum is hidden, things where the host galaxy is dominating the continuum, and things where basically the Lyman alpha forest is eating away at that continuum. And so I'm not really going to get into the differences between those, other than to note that all 4 of those categories of objects can benefit from machine learning algorithms and the types of things that I'm going to talk about here, but probably realistically sort of need their own algorithms. We would have sort of 4 separate machine learning algorithms to pull out those different classes of objects. So just to remind you, in the X-ray, right, bright things tend to be AGNs, right? If you've got a luminosity above 10 to the 42, that's pretty much going to be an AGN. But that is not at all true in the optical, where your bright objects are completely dominated by stars and irregular galaxies, and your AGNs are down here, right? And so, obviously, we're primarily an optical survey, relying a lot on the infrared and X-ray data, as Niel said earlier. But our first problem is sort of dealing with that. We will have X-ray data, as Niel has said already, for a lot of objects, E rho zeta, even maybe 2 or 3 million AGNs. And then something else that we will benefit from is a lot of the objects that we decide are worth taking spectra of or identifying as AGNs will already by that time have spectra, either from SDSS or DESI or Foremost and so on. And so our training set will obviously increase in size with time. Okay, so using all the data, I would argue that most of us in this room, when we do AGN selection, we're throwing away a lot, if not the majority of the data that we have available to us. And we're just doing selection by colors or variability or X-ray, or maybe 2 of those combined, but probably not 3 or 4 or 5, different data types. And we can't really afford to do that with LSST, right? We have the data, we should use it. That generally says you need to be doing machine learning type things where you can combine data types that are very different in a way that is handled nicely with machine learning. And so I've been advocating, this sort of kitchen sink approach where, we're going to do magnitudes and colors and morphology and multi-wavelength, astrometry, proper motion, variability, basically all simultaneously. Put all those types of data into one algorithm that then generates your AGN candidates. So Paula already went through some of this, and I'll just go through it again. But here we have a color plot where the quasars are in blue and the stars are in red. And then these other panels are showing that same color plot, but color coded by the variability parameters, right? And so what you can see is that when you can combine 2 things together, the colors and the variability parameters, you're doing much better than just doing one by itself, because the quasars and the stars are obviously varying quite differently. And then when we combine those 2 things together, we're going to do a better job of picking out the quasars, right? And so if we can then layer on astrometry and multi-wavelength data, we would do that much better. And so with variability, obviously, what's happening essentially is that normal stars aren't very variable. Variable stars have a large variability amplitude, and so we can distinguish between those. And then the quasars and AGNs on top of that have a different variability amplitude than the stars, and the timescales are the properties are different with different timescales. And so we can separate these things out fairly nicely. This I've stolen from Franz. I can't remember where it's from, but I mean, kind of shows what we all have come to realize, and what Paula was showing earlier and Niel showed before is, when you do different types of AGN selection, you don't always get the same thing. If you do radio and X-ray and variability, you're going to get slightly different things. And so it really is sort of key to combine all those things together. One thing that most of you know, but a lot of people I'm really sort of seeing in person for the first time, instead of on Zoom. And so you may not have heard me proselytize about differential chromatic refraction. So I'll take a minute to do that. So you may not realize how much basically chromatic dispersion there is as the light from your object comes through the atmosphere. So your object at an air mass of basically a 45-degree angle is actually dispersed by 60 arc seconds from where it is on the sky. And then the UGRIZ bands are actually shifted by like an arc second or two. And you have no knowledge of this because the astrometrists in your collaboration have fixed this problem for you and haven't even told you that they've done it. And you haven't even thanked them for it, but it really is a big deal. But basically what this means is the atmosphere is basically a spectrograph that you can use to identify objects, do photo Z and things like that. And so the idea here is that the U band and the G band are offset, and if you had so this is basically assuming a uniform amount of light in the U band and a uniform amount of light in the G band across them. If your U-band observation had an emission line that was in the redder part of the band, so towards the green, this blue point would shift down a little bit. And if your emission line was in the bluer part of the band, it would shift up a little bit. And so that's information that all of us are throwing away. It's hugely important for photo Z. It does a fantastic job of identifying quasars at like redshift 2.6 as they cross through the stellar locus and so on. And so it's something that I'm hoping to be able to take advantage of in LSST. It's not entirely clear how we're going to be able to do this, but this is a slide from Ian Sullivan at UW. And so he basically thinks of this in terms of subband imaging. So here's the basic idea. Take the G band here and split it into two, right? So sort of the subband A, subband B. Those images on the sky are going to be circular. But if there's a difference in the distribution of light between those subbands, like there's an emission line here, but not an emission line here, they will be shifted on the sky from each other. And so when you actually take your actual G-band image that includes both of these, it's going to be elongated in some direction. Okay. And then as you're scanning your objects on the sky, they're changing basically what the parallactic angle is. And so your object is going to get distorted in a slightly different way for each of your observations. And so that's what he's indicating here. And so basically you can take advantage of that information over time and all these different parallactic angles to essentially split your the U and the G band into subbands. So basically, one of the things we would hope to be able to do is not just report UGRIZY, but report like U1, U2, U3, G1, G2, G3, and then RIZY. Okay, and so that would be the easiest way to take advantage of that. It's unclear that the project will actually give us that information, but I mean they've basically promised not to hide the information from us in the PSF, which could also happen. Basically the information is there, but it has to actually be reported to us. Anyway, so I'm excited about that possibility. And then, so the point here is that what we would like to do is combine the colors, combine the variability, combine the astrometry, combine the multi-wavelength data, and then do the selection essentially all at once. Okay, so that leads me to talking about machine learning, right? So we've got data that has lots of different units, doesn't really go together. We don't want to make cuts. We want to sort of do things probabilistically and put it all together. And so when we're doing machine learning, we need training sets. So what we have is some 469 million SDSS objects, which is large, but we're going to have 40 billion LSST objects. So already that's not quite big enough training set. But then what's in the data challenge is 750,000 quasars from SDSS DR16. Actually, that's not even true. There's like 170,000 or something like that. 1.8 million galaxies, 385,000 variable stars, and so on. And so that's not very big, and the sample is somewhat biased. So one of the things that we have been talking about doing in my group is not just machine learning, but specific types of machine learning that can account for this, particularly using autoencoders and transfer learning. And I just highlight a nice book that goes through some of these kinds of things there. So Paula has already talked about autoencoders. She actually went into variational autoencoders. Let me take a step back and just explain what an autoencoder is in the first place. So it's something that looks at the input, reduces the dimensionality of that input, and then basically expands that that information back out, and then compares what you put in to what you got out. Okay, so it looks like a neural network, but with the same number of inputs and outputs. So this is actually an example from imaging, where you've got 28 by 28 pixel images, and so there's 784 pieces of information. You might think that's a lot, but there's actually 387 columns in the data challenge data set. So it's not totally crazy for what we're dealing with. So imagine I've got 40 billion LSST objects, and I've got something like 400 parameters for each of those objects. So what am I going to do? I'm going to take those objects, those 400 parameters for each object, and I'm basically going to say, okay, those aren't 400 independent pieces of information. There's probably only like 10 dimensions that matter, right? So all of those 400 things aren't, telling me something different. They're all correlated in some way. And so what we're going to do is basically degrade the resolution down to, in this case, 30 parameters. Quasars, 2 or 3 parameters if we're just trying to distinguish between different types of quasars, but maybe 10 parameters if you want to distinguish quasars from stars, from galaxies, and so on. Anyway, so you take your high dimensional space, you reduce it to a much lower dimensional so-called latent space, and then you expand that back out. So you're erasing most of the information, but then expanding it back out to the original, say 400 parameters that you started with, and then you're saying, okay, well, how similar did these parameters that came out look to the parameters that come in? And that's basically telling you, how well this lower dimensional latent space is representing the data that you fed into it. Okay, and so it's basically just a dimensionality reduction technique. So what we really then want to do is take all of the objects. Okay, so problem is our training set is small and not representative. And so what you want is a method that literally uses all of the data in the training set. So we're going to take 40 billion LSST objects with 400 parameters, and then basically run that through an autoencoder. Okay, and so what that does then is says, okay, I've got some 10-dimensional data space. I've got a clump down here, I've got a clump up here, I've got a clump over here, and I've got a clump over here. I don't know what those clumps are, but I know they go together, right? And then you're going to use that information, that basically classification, coupled with your smaller biased labeled data to then identify those clumps. Okay, so you might say, okay, so I've got these 4 clumps, I don't know what they are, but based on the label data, these are low Z AGN, these are high Z AGN, these are galaxies, these are stars, and so on. All right. And so that's illustrated here. So basically, you train an autoencoder on all of the data, literally all of the data becomes your training set. And then with what you're trying to do is figure out the best way to go from very high dimensions to lower dimensions. Once you have that, now you are hooking that up to your labeled data to do your classifier, right? And so that's a simple autoencoder. What you would like to do is more like what Paula was showing, a variational autoencoder, which gives you a little bit more flexibility in your implementation. All right, and then the last thing is I want to highlight Drexel's work from the data challenge. One of the nice things about the data challenge was sort of learning what other people are doing. The stuff that my group has been talking about, Drexel in Serbia has basically already done at a high level. And so I was really excited to see that. And so one of the things he was doing is using these variational autoencoders. But I also want to highlight their use of this extreme gradient boosting algorithm to solve other problems that we have. So the first is the data space may be sparse, there can be missing data. So, you know, Gaia only covers the brightest objects. You might have some epochs that are missing. Say a spy satellite has gone by and you had to throw away the data or so on, right? And so, you know, there's various reasons, or maybe your classification used like one-hot encoding. And so you've got basically, you know, a lot of just blank fields amongst your data. And then now you've got a problem with speed and data volume to deal with. And so something like this extreme gradient boosting algorithm is really helpful there. And then, you know, really my point here, and part of my question to Paula, is we can talk about this afterwards, is scikit-learn is a toy. Is a toy for learning. I use scikit-learn in my class to teach people how to do machine learning. It is not something that we're going to use for LSST data classification, right? I mean, I've broken scikit-learn with 50,000 objects before, right? So what we need is algorithms, and this is something to talk to Neven about and Link, right? Is how we actually have algorithms that can handle, you know, what we actually need and what we want to do. Okay, so that's pretty much it for science stuff. I'll just highlight, you know, our solution in my group at Drexel used autoencoders. Ash Karale here is with me. We're working on basically trying to figure out how to integrate those different approaches. We should talk to Paula about how to integrate approaches there. That has been slow because there's, you know, no funding to support it, right? So that leads me to last slide that we can talk about in terms of like LSST structure and leadership. And this is sort of goes to Niel's talk earlier and Matthew Temple's question. I probably will step down as one of the co-chairs, in part just because there's no funding and I need to concentrate on the things that I need to be doing, you know, to get funding. But I think it also, you know, is good to sort of shake things up every once in a while and recognize that it may be that people in Europe or in Chile are in a better position to do some of these things. And so I don't know, I'm interested in talking to people about that. What's the best way to structure the leadership of the AGN science collaboration? You know, what's the best way to get more junior members to step into leadership positions? You know, as Matthew mentioned earlier, there's not that many full members. We should really be encouraging people that are actually actively doing things to become full members. What I said earlier was the idea was that if we had money coming in to the AGN science collaboration, and you would have to be a full member for it to go sort of back out to you. But since we don't have any money, that hasn't really made sense. But you can still get credit in terms of job market and things like that for being a full member. We do have another level of membership, a core membership, which is the idea that, you know, you would then have rights to put your names on your name on science collaboration papers that are sort of developed communally and so on. And so, you know, we should do more there. And then, you know, finally, you know, something that Niel and I have been emphasizing is, you know, the junior people in the room and online, like, don't wait for us to do stuff, right? I mean, there are things to do that will benefit you in your career, like just go do them. You know, you can certainly let those in the leadership of the science collaboration know what you are able and willing to do. But I would honestly encourage you, you know, just sort of do it, right? So one of the nice things that worked out really well about SDSS is that there was, as Niel said, nobody is allowed to stake claim to things. And I think LSST is going to basically work in that same way. So even if there's two groups doing exactly the same thing, I think that's okay, right? Like no two people in this room are going to write the same paper. If I give you a title of a paper to write, you know, you and you're going to write totally different papers. And so it's okay that, you know, people are sort of working on the same things. So, you know, just go do it. Don't worry about stepping on people's toes. If you're thinking that, oh, somebody else has the market cornered on that, I guarantee you that is, you know, not the case. We will all be excited that somebody else is actually, you know, doing something. So, all right, I'll stop there.
Any questions?
My question is more related to the astrometry part you talked initially in your talk. I'm actually wondering, like, how do you plan to split the data? Is it going to be like 50-50? I'm just wondering, like, you know, if the emission line is also divided half and half, if we, like, have you given some thoughts on splitting?
I'm not sure what you're asking.
I'm asking, like, when you plan to divide the data into subsets for astrometry purposes, how are you going to make the division?
I'm not.
It's all based on.
It's all empirical, right? For first order, I'm assuming I don't know what any of these objects are.
Okay.
So I don't know where the emission line is. I don't know where the redshift is, right? So at least that, in my vision of things, right, is you treat all of the data as your training set.
Okay.
Right? And so I wouldn't split objects. What I would expect to come out is my 10-dimensional data space, you know, objects at redshift 2.3, which have an emission line to the right hand of the G band, are going to be slightly offset from objects at redshift 2.1, where the emission line is, you know, in the left hand of the G band. And that when you then overlay your labeled data set, you will then identify, you know, not just, oh, this is a likely AGN, but this is a likely AGN at redshift 2.3. This is a likely AGN at redshift 2.1, because the astrometry is telling me that that's what's going on.
Okay. Well, I feel like, you know, that's one of the parameters where the selection effect would also be important. And I think it's also important to watch out for that.
So also about that, so it's really interesting, this idea of using decomposition of the PSF. But I was wondering, have you thought about, so it's going to take a long time to build enough air mass, and enough time might mean that the AGN will actually vary throughout that process. So how does that impact the process?
I mean, it will impact things. So I don't really know what's going to happen with the DCR. Haven't gotten anybody to commit, right? So SDSS handled this by just measuring the position in the U, the G, and the R band, right, because they were basically simultaneous, right? With LSST, that won't be quite the same, right? I mean, I talked to Robert Lupton about this a couple of months ago when I was in Princeton, right? And I mean, he assures me like, oh yeah, you're going to get this information, but like I said, no one has indicated how that will be. So Ian's sub-band evil plan will take time to do, but I think there's DCR information, you know, really just even in a single epoch of data. So like how we're going to make use of that is going to depend on how that information is going to be provided to us, right? But I think the subband thing is the easiest thing because no one really has to even think about it. You're literally just going to get 3 subbands. I think we will have other information that you can just throw into the kitchen sink. Right?
Yeah, I guess I'm worried on building the subbands on variable sources. That's the.
Yeah, I mean, it'll matter, right? So how it'll matter, I don't.
So just following up on that, surely you've got a bunch of stars in the field at the same time, right? So you can measure the differential offset for each pointing, for each exposure, and build a histogram of effectively the power law slope across the band at a single moment in time, right? You don't need multiple epochs to do that.
Right, but because it might take a long time, you're not guaranteed that the source is on the same state when you observe it this way than this way, right? So I think that's my
I
concern.
think you'll have enough epochs that'll average out, right?
Okay.
Yeah, if this is an interesting topic, we can leave the discussion to later. And I want to know if there are any other questions. Yeah.
So during the middle part of your talk, I guess you had this. You were discussing the various features. You were discussing the feature space and how there would be these clumps in this potential 10-dimensional space, and then you would assign labels to those. I presume you're planning to assign labels to those based on well-studied fields like the deep drilling fields and such.
Yeah.
Do you think the deep drilling fields are going to be sufficient in terms of numbers of sources, in terms of the quality of characterization there? I mean, a number of us are working hard to build up the deep drilling fields, but in my opinion, there's still actually quite a ways to go. So do you think they're going to be ready? How many objects do you need? How well do they need to be classified and such?
I think that depends what your goal is at some level, right? So, I mean, if we're going to do classification and photo-Z simultaneously, right, then probably not, right? Or I'm sort of, if you just want to do like, this is an AGN that doesn't have the Lyman alpha forest in any of the bands,
right?
Then maybe that's the deep drilling fields are okay, right? But I mean, like, what do we really need and want to do this right? I mean, we need spectroscopy of every W2 source on the sky.
We hope to give you about 12,000 AGNs.
Yeah.
That are well characterized. That's about what can be done.
Right.
With a lot of effort.
Right.
Is that kind of a sounding promising, or is that it's going to be too sparse?
I mean, my attitude is we just have to start working with stuff and doing it, right? I mean, this is the frustration with like grant funding for this, right? We sort of get a lot of like, oh, have you thought about this, and this, right? It's like, well, yes, that's what we would do as part of this 3-year program is worry about that exact thing, right? Okay. So I guess in my mind, we just need to start and find the answer to that. I can't make more objects in the training set than there are.
Right. I just imagine distributing 12,000. If it really is 10 dimensions, distributing 12,000 objects over 10 dimensions, it's going to get a little.
Yeah. So it's not enough, right? But I mean, we can start with 3 dimensions and sort of bootstrap our way.
Yeah, I guess this is a very exciting topic. And thanks, Gordon, again. Our next speaker will be Ivano Sashil. Ivano is going to talk about selecting higher redshift quasars with machine learning.
Hello everyone, I'm Ivano Saccheo. I'm a PhD student from the University of Rome 3, working in collaboration with the INAF Observatory of Rome. And today I will talk about using machine learning to select high redshift AGN, and also more broadly to select AGN against other kind of sources such as stars and galaxies. Okay, I don't think I have to explain why using machine learning is important nowadays. Astronomy has long entered into the big data era, as you can see from the number of published papers using machine learning or neural networks or whatever in the title. And this vast amount of data poses serious challenges to classical analysis methods. And as also Gordon Richards already explained, thanks to machine learning, you can fully exploit all the available information in this data. As I was saying, my project involved 2 kinds of analysis. But the first one, we want to select bright high redshift quasars optically luminous from stars and galaxies and lower redshift sources, while in the other one, we want just to select AGN from galaxies and stars. So since we want to achieve 2 different tasks, we made use of 2 different samples. Now, the first sample was kindly provided us by the guys accredited there, working in the Observatory of Trieste, and it is composed by 80,000 AGN selected from the Pan-STAR survey. This sample is mostly composed by type 1a quasars, and just 0.3% of these sources are nearby local Cipher and type 2 AGN. It is composed by very bright sources with a Y band magnitude below 19. And for all these sources, we have a spectroscopic redshift. Here you can see the distribution. And we label as high redshift AGN those with a redshift above 2.5. And they constitute roughly the 10% of all the AGN in this sample. To this AGN sample, we also add, apart from the Pan-STAR's bands, also the Gaia bands, which cover more or less the same wavelength interval, and also the WISE-1 and WISE-2 bands from the CatWise catalog. We assembled also a parent sample composed by stars and galaxies. Stars were selected from the Gaia catalog according to their parallax and proper motion, while galaxies were selected by cross-matching with other pre-existing catalogs and also based on their extendedness. To be included in the final catalog, we requested for both stars and galaxies to have photometry available in all the bands, so in the Pan-STARs, Gaia, and WISE-1 and WISE-band, and we also applied the same cut that was applied to the AGN sample. So this leaves us with the final sample, and you can see the distribution in magnitudes for all the three classes of objects, and we constructed a balanced sample. So we have a roughly equal number of stars, galaxies, and AGN. Our method to select AGN is based on having two classifiers. The first classifier is devoted to distinguishing between stars, galaxies, and AGN, while the second classifier is trained on the AGN-only subsample and is devoted to distinguishing between higher and lower redshift AGN. While we test the full pipeline, we just simply put the full test sample into the first classifier, and then sources that are recognized as or predicted as AGN are distinguished between higher or lower redshift sources. We tested several supervised classifiers. Of course, the random forest, which is the golden standard among the machine learning classifiers. So it can give you a baseline of the result that you hope to achieve, and also it accepts unbalanced samples. But I want to spend a little bit more word about the probabilistic random forest, which is a recent improvement of the random forest. And differently from a random forest, you don't have in each node a binary classification, so the object gets propagated either to one branch or to the other. It gets propagated towards both the branches with a different probability. So you will end up with, in the final leads, with a probability of the object in being there. This is in reality just for the ideal case, because for computational limits, branches which have a probability lower than a certain threshold get pruned, and so the object cannot propagate it there, but still you have a different probabilities. And one important thing related to the probabilistic random forest, and since the features are treated as probability distribution, you can input errors on your associated data as a distinct kind of feature, not like another feature that classify as to recognize as the uncertainty on the related data. Then, of course, we tried a simple the artificial neural network in the multi-layer perception, which is the most simple neural network that you can construct. We just use one with 8 hidden layers with 8 neurons each. We try also several different architectures, but we saw that the results were not greatly affected by the architecture of the layer. And then, of course, one of the many gradient boosted classifier that are now very popular because they seems to outperform the achievements of the random forest. Here I show you just the routine pipeline and the result, and I take this opportunity to explain some of the terminology I will use in this talk. So when I talk about the recall, it's the ratio between true positives and the sum of the true positives plus the false negatives. So it gives you the completeness of your results. When I talk about the precision, it's just the true positive over the true positive plus the false positive. So it gives you information about the contamination. The contamination is just 1 minus the precision. Okay, here I show you the results of the first classifier, so the one devoted to the selection among between stars, galaxy, and luminous quasars. And we did this test by sampling for 100 iterations the testing sample to get a mean value and a standard deviation. And we can see that basically all the classifiers for these particular samples are excellent to selecting all the AGN with a recall close to 100% and very little contamination. While for the second classifier, the one which is devoted to distinguishing between high redshift AGN and lower redshift, we still have, apart from the neural network, we still have a quite good call. We select almost all of the high redshift quasars, but we have a much higher contamination and above 40% of contamination. So we looked at the source that were predicted as high redshift quasars, but which are not, and we can see that they are mostly composed by still AGN sources, and indeed they are sourced with most of them are sourced with redshift between 2.25 and 2.5, so just a little below the threshold that we put to classify an AGN as an high redshift source. So the situation is not really dramatic. But since we want to have a higher precision, I must remember you that actually each classifier doesn't give you an unique answer about the classification, but it rather gives you the probability of a source to belong to one particular category. So if you play with the threshold, you can have this curve recall against precision, and depending if you're interested in having a cleaner sample, you can put the threshold dagger values and be here, or if you're interested in detecting all the sources, high pressure quasar, you can have a lower threshold. And there are no decisive recipes. Here I show some examples, and basically prefer this magic quire, which is basically the threshold that maximizes the F1 score, which is simply the harmonic mean between the recall and the precision. Okay, we also try to see how our results were affected by the number of bands and available for our sample. And we can see that if we use only the pan-stars bands, we get results quite not very good, but they can improve and they can really be improved by using optical bands, of course. And there is no difference between, not great difference between using also the Gaia bands in addition to the pan-stars ones, basically because they are embedding the same information, covering the same wavelengths. Okay, so I move to the next topic. Of course, this sample was devoted to selecting bright redshift, high redshift quasars, but we know that actually the majority of the AGN is composed by obscure and lower redshift AGN. So we try to assemble a sample which is less biased against the obscure population of AGN. We did this by making use of the X-ray catalogs with 3 different fields with different height and different depths. so the XMM, XXL field, which is wide, but not very deep, the Chandra Cosmos legacy survey, and the Chandra Deep Field South. And we made use of the optical counterpath catalog. And then we added a parent sample of galaxies. I showed you the luminosity against the redshift of the 3 samples of the AGN. And then we added galaxies by looking at already published multi-wavelength catalogs or by joining by ourselves data from different surveys available on that fields. To add a galaxy in our parent sample, we did some requests. We request them to have an estimated redshift, either spectroscopic or photometric, and it was chosen because we wanted to be sure that given the redshift of the galaxy and the flux limit of that particular survey, the galaxy wouldn't have would have been detected if they had an X-ray luminosity above 10 to the 42 per second. So in this way, we are sure that they are not X-ray AGN, let's say. And also we removed all sources within 7 arcseconds from X-ray sources with not confirmed optical counterpart. In this way, we don't achieve a complete parent sample of galaxy, but we are quite sure that it is cleaner and it's composed by only galaxies. This, of course, comes with a trade-off, and indeed you can see that. That we are missing most of the galaxies at higher redshift. So for the moment, we are limiting our analysis to sources with redshift below 1.5, even for the AGN population. Okay, and since the different multi-wavelength catalog from the different fields have different multi-wavelength coverage, we assembled, let's say, mock multi-wavelength catalog, in which, for example, we have this G or visible band, which is given by the intersection of the V and G bands, or the mean infrared and mid infrared through magnitudes, which are provided by either Spitzer channel 1, channel 2, or WEX1 and WEX2. And here I show you the number, the percentage of sources with the data in that particular band. So this is the result that we get. We, as I say, I assume to classify, it's just a binary classification, either a source is an AGN or it is not. And I put a threshold to select a source as an AGN of 0.6 in order to achieve a precision of roughly 80%. And we get a completeness of 84%, which is actually really vary depending on the obscuration of the source. Indeed, if we look at the distribution and age, and we, let's say, call as type 1 AGN and those with an age below 22, we can see that we can recognize most of them, while if we look at the population of obscured quasars, we get worse result, as expected, of course. We did the same test that we did with the classification of high-redshift quasars. So we looked how our results were affected by the number of bands available. We can see that with the LSST bands, we by adding do not get a very good result, but by adding also Nuclei-like bands, we can greatly improve the results of our selection. And then adding, of course, the mid-infrared bands can lead to even better results. Of course, these are the record that we get for us by assuming for each classifier a precision of at least 80%. And I want to show that actually what the number of bands affect is really the number of type 2 AGN, let's say, that we can recognize. You can see that the histogram in the left part of this plot are not not really different, but we can select less and less type 2 AGN with less bands. Okay, what about the next steps? Of course, we know that every sample is biased in some way, and we cannot risk to paint this bias towards the the upcoming data. So we need for sure to validate our results with other catalogs and to check whether the same results apply to these catalogs. We are thinking to use the mock catalog that we are building as part of the in-kind contribution, and you will hear more about in tomorrow's Arcade panel talk. Another idea was using the data challenge sample, which has been released recently, and I'm open to other suggestions. And of course, we want to, in the future, we want to include viability, because we know that it is one of the strengths of LST future, and also to use directly images. And so with some kind of convolutional neural network and to increase the number of features. Here I leave you with my take on messages. Basically, we check that all the supervised classified equity tests provide more or less comparable results. We use the gradient boosting because it's the more flexible one. We are very able to recognize, thanks, we are very good at recognizing all of the bright type 1 quasar. And we have contaminants which are not, they are mostly composed by still higher redshift AGN, just a little below the threshold we put. The selection of type 1 AGN is much more efficient than the selection of type 2. And LST bands alone are not sufficient to achieve optimal result. That I think is quite remarkable, at least just with colors. And by the addition with the Euclid or even better, wise and different bet can greatly improve our results. And as next step, of course, we need to validate all of these results.
Any questions?
Would you put back up one of the cat boost slides that has the confusion matrix?
Yes. One, I guess.
Yeah, sure. So I think this partially answers Niel's question. I want to see if you agree, right? So if you had 12,000 objects in your training set, right? Basically what that means you can do is you can do a pretty good job on star, galaxy, low Z, high Z, but you're not distinguishing a redshift 0.5 low Z from a 2.2, and you're not distinguishing a YSO from a supernova, or, you know, things like that, right? And if you wanted a higher degree of, you know, subsampling, you would need more objects in the training
Yes.
set. Would you agree with that? I mean,
I agree. I also one of the points is that we train both of the classifier using different. You can see, so the second classifier was also trained using a balanced sample of high redshift and lower redshift. When we put all the full sample, the lower the high redshift quasars are just a tiny fraction of them. So I think it also affect the results. And yeah, I also. Yes, of course, we need a larger sample, of course, to.
Just a comment on that. So I highly recommend all of you to check the imbalance learn package, because then with that, only with one line of code, you can solve that problem. And actually in Alerce, we have a classifier that is able to select superluminous supernova with a sample of only 20 versus 2000 type 2 or type 1. It's super efficient, and it's just one line of code. The only difference is instead of importing scikit-learn, you import imbalance learn.
Yeah.
And you don't need to balance by hand.
No, but I think that the random forest by scikit-learn already accept unbalanced samples.
Yeah, but
it's not okay.
No, it's because it's just weighting the weight.
Yeah, okay, yes.
With the imbalance learn, every tree sees a balanced version, but at the end you see the whole.
Yeah.
And also, if you plan to use other classifiers like multi-layer perceptron, there are mini batches generators in the same imbalance learn package. It solves totalization, so I recommend.
Thank you very much.
Any other questions?
Can you go to the slide where we're showing the distribution of NH values?
Yes.
So, because it seemed like you were recovering a lot of high NH sources just using LSST data.
Yes, okay. I need to say that it's very preliminary. I was also surprised. I think that most of these camps of partners, we know the ratios and we are removing the sources above 1.5. So maybe that helps in recognition. I don't know. I'm also surprised by this kind of result, and that's why I need to validate using other catalogs, because I wasn't expecting either to get this kind of numbers. There's also the possibility that they are not. I mean, I have not the optical classification for this source because there is a sample assignment from X-ray source, even though okay they have the multi-wavelength data. So maybe a bit of a population in that range of NH is composed by optically typed quasars, but I don't know. Yes, I need for sure I need to validate because it wasn't. I must be honest, wasn't expected.
Well, I mean, did you do all? You try to do all the X-ray sources, right?
Yes, the one with the optical content.
They're not mostly type 1 quasars. There are some broad absorption line quasars, for example, often have quite heavy X-ray absorption, but the majority of those are going to be type 2 or otherwise elusive AGNs. I know those fields fairly well. I know what's in the
I show you the multi-wave catalog I am use.
Yeah, we made one of those.
Any more questions? Anything online?
No, not yet. Yeah, that's one.
Yeah.
Yeah, just curious. You mentioned that the importance of the mid-IL geometry, but when LSS is start operating, what would be the most promising data set we can actually combine with LSS to get the similar exercise?
So what?
The mid-IL data.
Okay. Yes. I don't know. I guess you cross-relate with, but I guess all the waste bands are already. Waste source are already cross-matched with already known sources. So I don't know whether with LST you will be able to have also the mid-infrared data for all the sources that will be co-set.
Okay, I guess I'm wondering, do we have enough data or do we need an extra follow-up?
I guess hopefully we will need the extra follow-up observation. I don't know whether they will be provided. But of course, the mid-infrared, at least in my exercise, has proven to be really important. I can see.
I have a quick question. Would you mind going to, the first part of your talk, I think you mentioned different machine learning techniques and there are some comparison between them, right? So I'm very excited to see that all of those works, and I guess there's a test with different bands available, and seems like MLP doesn't work as well, as good as others. So my question is, since have you considered the signal to noise of the data and how does that impact how these algorithms work? Because as you mentioned, for example, probabilistic random forests take into account the error of the data, right? That maybe when we go to noisy end of the data, it will show some difference compared to other methods. Have you investigated that?
No, not at the moment, no. The point is that for this sample of, let's say, bright sources, I trust it very much because it was passed me by a guy already working on that. So, and it's composed by very bright sources, so the noise is not very relevant. But yes, of course, it is. It should be taken into account in the future. If these two projects were just, in particular, this one was just like a project that I made to take confidence with the machine learning in my first year. So I don't have very expertise this kind of.
Thank you. Maybe last quick question, if there's any. If no, let's say.
Just the friends made a comment in the Zoom. He mentioned that it's important to remember to interpret the contamination rates and need to convert it back to the unbalanced base rate.
Nobody is.
Okay, if there's no more questions, thank you, Manu, again. That concludes our morning session.
One paper on rolling things, why don't you start with that?
Yeah.
I'm gonna go to page 3 of this document.
The arrow doesn't work. I was wondering how, it's fine. Not a problem. I don't know how the arrow works. It doesn't work. I don't know. What do I do?
This whiteboard thing is a flip, just this page of flipper is a whiteboard.
Yeah, I got it. Okay. I'll use that proportion.
Okay, so we have a couple of discussions built in. We have some sort of plans for them, but kind of want to see how things are going to go. So among those things that we're looking to talk about are basically survey cadence, making sure that people in the room understand how LSST is actually going to work. Some of that is still up for decision. We're going to spend some time talking about posting of projects, and then maybe spend some time talking about the AGN Science Collaborations roadmap. Okay, so we've got 3 different discussions over the next 2 days to do that. We're going to start with the survey cadence stuff today. If that ends up taking the whole hour, great. If not, then fine. So
can we do a poll to start with? I mean, may I ask how, if you have read this document in some decent way, please raise your hand. Okay, well, it seems like discussion is worthwhile.
Right. So that's kind of what I expected, right? So I posted this to the Slack. We can post it wherever anybody needs it. Basically, at the very least, you should sort of read through the top level recommendations. That's what we're going to try to go through. It may be that it makes more sense for us to go through it like a little bit today, let people read it tonight. Don't drink too much at the banquet, and then talk about it, tomorrow, and we'll see. And the same thing for the project posting. We should say that Franz Bauer is the one that's actually the expert on this. He's on the Survey Cadence Optimization Committee. He's on the Zoom, we hope. And can maybe fill in some details. And so Neil and I are going to try to do the best that we can here. Everybody good with that?
Is everyone happy with that plan?
Lay
Or
around.
is it, if this is dreadfully boring, speak up and we'll do something else.
So
Okay.
Okay, good. Let's do that.
So should I start with like a basic overview of rolling cadence type stuff?
Yeah, sure. Here you go. And we need to go to the next page if we're going to do rolling cadence.
I don't even know if I'm going to use this quite
Okay,
yet.
that's right. Well, it's here.
Yeah, fine. Okay. One way to do time domain is to have uniform cadence, right? We're going to observe every day or every 3 days or what have you, right? Some groups don't like that very much, particularly supernovae people, because supernovae basically go off and fade away in 180 days. And so you want as many observations as you can in that 180-day period. And so they would rather blanket some fraction of the sky at very high cadence and find all the supernovae in that part of the sky and completely ignore the rest of the LSST survey. And in fact, they have done white papers definitively showing they get, 10 or 100 times more supernovae if they do that, okay? So for AGNs, what we are concerned about with variability is time scale analysis, essentially, right? So at some level, we would like the same thing that the supernovae people would like, because we don't necessarily want just every 3 days, because maybe we want some observations spread out over a longer baseline or a shorter baseline or so on, right? So one of the things that Wei-Feng, you and I did was sort of write a little white paper showing that extreme rolling cadence is terrible for AGNs, whereby you just focus on one part of the sky and totally blanket it. But some mild level of rolling cadence is actually really good for us. The problem with extreme rolling cadence, I guess the way I can illustrate it is, if we did 1,000 observations today, right? And then we did one observation 1 year from today, then we have aliasing. We've now got 1,000 baselines that are exactly 365 days. And we don't need 1,000 baselines that are 365 days. We would rather have, one at 365, one at 300, one at 250, one at 270, one at a half day, one at 3/4 a day, and so on, right? So for AGNs, what you really want is a uniform distribution in log delta t. We're not going to get that. Niel has a plan called an accordion cadence
that's for the deep drilling fields only, though.
For the deep drilling fields, it kind of does that sort of thing. Anyway, so in a nutshell, that's sort of that's what a rolling cadence is, what the issues are for us. And so what the Survey Cadence Optimization Committee document does, it sort of goes through what their exact plans are for how this is going to work. And I don't know if you want to take it from there.
Okay, well, the only thing I would add, so I think Gordon has summarized it very well. So the only thing I would add is that, so what they plan to do is they plan to take the available sky and split it in two, right, by declination. And one part of that, one half of that gets 90% of the observation time, and the other half gets 10%. That's called the rolling weight. Okay, and so that, this has, I think, already been declared, except if under certain simulations there are problems with static sky cosmology and some other things, in which case they will reevaluate it. But the ship has largely sailed on this one, but we would like to know if anyone is extremely unhappy about that. You wonder the implication of that.
Just to clarify.
Yeah, go ahead, Franz. Go ahead.
So what that means, right? We have, for the wide fast deep, we have effectively 800 total observations over 10 years. So that's roughly 80 per year, right? And so this 90 and 10%, what that means is that in half of the sky, you're effectively going to have 8 observations in a season over 6 filters. Right? Or is that right? 80, sorry, should be 80. I can't do the math. 80 over 6 filters. So you, in effect, you're going to have, one every week, every, sort of 20 days, something of that order. And so then the other part of the sky will effectively be double, because you're taking, what was already going to be there, and you're adding the extra 40% onto that. So it'll be like 1.9 times what it was originally. Does that make sense?
Yep. Okay. So are people happy with that? Is anybody unhappy? So I saw you had raised your hand.
Yeah, so it's not about happiness or unhappiness. It's about also like capturing the fastest possible variability, right? So I was wondering if in the plan, even for a certain period of time, there could be like observations sampled at like on few second scale and continuous monitoring for like for some hours that could be included.
So can everybody on Zoom hear that? Franz, can you hear that?
Yes.
Should I repeat the question?
No, the sound is really good in this room.
Okay, good. So I think that actually is really more for the next point. I'm talking about intraday observations. So let's hold that for a second, right? I would say I am very unhappy with this, right? I think that's a mistake, or at least for the AGNs. I think I can't remember who showed this at I don't know, the AAS meeting or something like that, and like, oh, we're not talking about extreme rolling cadences, and I was like, well, anything over 0.8 I would call extreme for AGNs, in the sense that it causes this aliasing that I was talking about, right? It's too clumped up. But at some level, we're at the mercy of what makes sense, for everybody else, I think. It's worth noting that there are simulations, it takes a little bit of effort to get involved in that, to understand them. But these are things where you don't really get like an opinion per se. It's more like, here, look at the simulations and see what they're producing and see what metrics they're producing, and then look at that and sort of say, okay, can I do my science with this? Because there's a lot of analysis that's basically already been done for us. We were asked to come up with metrics. I mean, nobody's getting paid for this, so we haven't done all the metrics that we would really have liked, but there are metrics there, and there's simulations that are done, and you can sort of look at these things, if it matters to you.
So one question. So, right, so it's half the sky, it's a faster rate. The other one is much less.
Yes.
And then that flips for the next season, and it just keeps flipping, or every 2 years will it actually change
No,
the
so
distribution?
the first year is normal because they actually want to build up templates.
Okay.
Then years 2 to 4 are rolling, and I'm not exactly sure how that works because there's only 3 years there. But then I think year 5 is going back to, I mean, at some point they need to have 4, 2 and 2 to even it out. And then at some point they go back to a uniform observation at year 5, I think. And then years 6 through 9, they do rolling again. And then year 10, they would go back to a uniform. That's the idea. So it's not even in every year that they do it.
I guess, Franz, Roberto was asking though, in a given, take a single year where rolling is activated. How do you flip back and forth between the 2 declination limits?
It's not 2 declination limits, it's actually 4 strips. But there's 2 on, there's basically a southern and a northern strip that are on. And then there's 2 strips that are off.
Yes.
And then they alternate between those. So it's actually
half season, it's at the middle of the season, you flip it the other way.
No, each season is on for one of those 2 sets of strips.
It's a full season. Yeah. The next season you flip it. Okay.
And the second time you cover this, and then the second time you do this again, so years, it seems like 6 to 9, do you actually cut it in the same way, or do you change the way you cut it? Okay.
No, it should be the same way. I mean, yeah, it's largely for, as Gordon said, for catching, getting better refined light curves for supernova.
Because since it's just for supernova, it might be worth considering sort of if you can change the pattern, at least so there's overlap regions that actually get sort of more continuous coverage.
What do you mean by continuous coverage?
Right. So you could imagine, so you have very high cadence on one side and not a lot of high cadence, right? And then you flip that. But the next time, instead of doing it like this, you could do sort of patchy like this.
Split it a different way.
Right. So then you have a zone that through more than one sort of season is actually observed at a higher cadence.
Yeah, we could try basically moving the zones as a function of time so that the longer term light curves don't get affected. No one has suggested that. It's potentially fine. You would want to try and demonstrate that it was improving some metrics in some way to sort of motivate something more complicated. But yeah, I mean, yeah, I would say it's certainly doable.
It seems like an interesting idea. So if you have interest in that, write up a note and send it to the staff.
All right.
One thing I will say on that. So Franz, you're saying it's basically 4 strips or stripes, right? Alternating.
Yeah. So the only issue, Roberto, is the uniformity. So there are other groups that would like what we call static science that would like all data releases to be as uniform as possible. And so doing that in a way that makes that possible is maybe trickier.
Well, I mean, so what I was going to say is, so I do have a proposal to do something different. So you can demonstrate that deck stripes are the incorrect way to do this.
Okay.
Right? It makes it easier to do the planning, but it's actually demonstrably wrong, right? So I did put in a proposal that it should be candy striped so that it basically migrates in RA with DEC. So you could imagine having your candy stripes shift to achieve what you're talking about, but we can talk about that offline. And I suspect it'll be too complicated for anybody to want to implement. But I think they did try to code that up or something. Yeah, Chris.
I don't know if this makes sense. I feel like we should, if they end up adopting this 0.9 and you're just flipping the declinations, I think we should call it wobbling rather than rolling, because it doesn't really seem like it rolls. If you wanted to really do a rolling cadence, wouldn't this value change? Like the first year they're getting templates, they want it to be, okay.
I think that one of the reasons why we wanted to start with this is just make it clear that what a rolling cadence means, because yes, the word rolling is not the correct one here, and so let's make sure everybody in the room knows what.
Yeah,
I suspect the ship is sailed. I mean, I understand where you're coming from. I think there's just probably too much momentum now to change it the same way that we still do magnitude backwards.
It's just maybe Franz knows about this, but like I thought that if you do this, then you're going to have these regions that are overly observed. Isn't that bad for dark energy science? Like,
what do you mean overly observed? I mean,
like doesn't that make certain regions non-uniform?
Supernova people are
per
happy.
season, yes,
Sure.
per season, but then the other alternate season, you pick that back up.
So yeah, okay, so we're like 10.
So every, on year 3 and year 5, the idea is that they would be even and you would have uniform coverage. And in fact, DESC is planning on having, one of the drivers is uniform coverage at these sort of year 3 and year 5 so that they can do intermediate science. So they have an expectation, and that isn't exactly true at the moment. And so there's a task force to effectively try and figure out how to get uniformity at these data release points.
Well, then, yeah, so then at that point, can we talk to them? Because I could see where it might help us a little bit, maybe, if like in the first year, it's how it's supposed to be, then it's 0.9, 0.1, and then, the next year they flip it, but then in year, I don't know, 4, then it goes to 0.7, 0.3, and then they flip it rather than always being 0.9. Then we get like a little bit more for AGN, a little less for supernova.
Well,
this is driven by DESC, and DESC needs a certain number of type 1A supernova, and right, that's it. So unless you can say that we actually are significantly hurt by that, and none of the metrics say that, then we don't really have a leg to stand on. The metrics that Weijing and Gordon put out actually don't really show strong differences between the rolling and non-rolling cases, because the detriment you get from having only 8 observations in a season, you get back in terms of having the double cadence in the other half. And so in terms of structure function metrics, it all kind of washes out.
I think so. I mean, the only thing I would say to that is I don't know that we spent enough time following up on that to make sure that that's true, but I can believe that it is. So for example, the differential chromatic refraction, I have been arguing that we should take at least 1 observation at the highest air mass possible. But then when you actually do the simulations, you realize that like 10 observations at air mass 1.1 is equal to like 1 observation at air mass 1.4. So my argument that we need high air mass observations like isn't actually true, just because LSST is actually so good that we're just completely swamped by that. So I'm a little nervous about the 0.9, but as Franz says, I can't really prove it, right? But if it is true that it's fine, then it's fine, because we just have so much data that it doesn't matter, right? But in theory, yes, 0.9 and 90%, 10% in one pair, and then 70% and 30% in another pair, like it has to be better for us. But it's the question, is it just epsilon better, and the supernova people now it's significantly worse?
Yeah, I mean, the thing is, like, you build up in a certain time bin, you build up better statistics, and so you pin that down better. And so the next bin over doesn't matter as much, right? If you're, say, trying to do the structure function. And if you're trying to get the slope, for instance, or just as an example, but you could have other metrics that benefit from that. And I think that's the issue, is that you get this extra slight benefit from just having better statistics in a given bin that helps you out.
Anything else on this? Because otherwise we should maybe talk about intranight stuff and just encourage people to go, read that.
Again, we won't belabor this too much because this is all available for you to read, but you should know what you're actually going to have in your hand. Okay, should we do the intranight one then? Okay, that one's on the previous page at the bottom. It's down here. Okay, you want to do this one? Go ahead.
I mean, I can start. So there are going to be visit pairs, and then one of the things that was discussed was, do we want to add a third observation?
Do people know what a visit pair is? First of all,
like 2 observations per zone?
Yeah,
2 observations. Yeah,
each of 15 seconds back to back.
But that's not enough.
Well, that's what you're going to get. Okay, to start with, that's what you're going to get. Now we'll come back and address.
Well, and in the U-band, just one 30-second observation.
Yeah, that's right. And yes, and there's in the U-band. So in all the bands but the U, the current plan is to have 2 15-second ones back to back. But there is a push to even take those 2 15 seconds and turn it into a single 30 to cut down overhead. But whether that will be implemented or not will depend upon actual data once the thing is operating.
Well, I mean, that is the default for the U-band right now.
That is the default for the U-band, but not necessarily for the other bands. But it could happen for the other bands as well. Last I heard, at least.
Okay, and then I don't know, somebody better other than me, Franz, maybe could talk about pairs or triplets.
I can say a little bit. I mean, it's here. So you're going to have these visit pairs, and there's going to be then a 33-minute gap, and then they're going to get another visit pair on the same patch of sky. That's not for us. That's not for us. That's for the people who want to track asteroids. Okay, there's good reasons for it. It's not our particular size, but that's
wait.
Go
So
ahead.
that second visit, 33 minutes later, is in a different filter.
In a different filter.
And we do want that. We very much like that.
Yeah, we like that part. Yep. Okay. Yeah. Well, that's what it says. I hadn't got to that. To be collected in different filters.
Is that so, Franz? Is that the Presto color, or is that something different?
No, this is just the standard thing.
Okay.
The Presto color is to have a third filter on the same night.
Okay.
All right. So everybody good on the visit pairs? We got 2 back-to-back, 15 seconds, and then 33 minutes later, another band. There's some rules about which bands should be paired, right? You don't do U and then Z 33 minutes later, right? So you do get 15 seconds and 30 minutes, right?
Now that you just then in addition to that, the stock is now recommending that you also want to have improved coverage on hours to 1-day timescales. And so what they're going to try to do then is come back and do a third nightly visit at several hours separation once every several nights to try to fill in that range of timescales, which was otherwise being poorly sampled.
Well, the thing is that if, the age, especially like the bright and variable AGN, if they are not continuously monitored for a given period of time, all of the interesting science that might be hidden there in the data.
I'm okay. I mean, this has been decided. The ship has sailed on that. I don't think you're going to get Rubin to spend a substantial fraction of its time pounding away with many 15-second observations for entire nights. I just don't think that's going to happen. Now,
except in the deep drilling fields.
Exactly. Yeah, maybe we can do something in the deep drilling fields for you, but aside from that, not so much.
Matthew, you have a comment?
I was just going to point out that this is all for the wide band steep, and that if you care about the high cadence stuff, we should be talking about the DDS.
The deep DDS, which we'll come to.
So anything more to say about the triplets? I mean, there's some details there that I think maybe matter.
So you will have
not in the summary.
You will have sampling on 15-second timescales. You'll have sampling on around 33-minute timescales, and now they're aiming to improve sampling on hours to 1 day timescales. They're going to be in different filters and stuff. Yeah, in YFSD.
And do you want that I talk a little bit about commissioning plans, which will give you some of that? Okay, so this is a little bit different. This is like main survey, but there will be science validation effort before the survey. It's probably 3 months, and there are 2 different proposals, but one of them, and probably the winning proposal, will be to look at 200 square degrees in 3 different fields where you will hit that each of these fields 7 pointings 1,500 times, which is so each part of the sky will get 25 observations per night, because you want to, in that 3 months, for these 200 square degrees to get 20-year depth. So, you know, and there are 3 fields. One will be, is it galactic plane, one is solar, and only one is extragalactic, which will be most interesting for AGN. So you'll get 7 pointings, 9.6 square degrees per pointing, you know, 65, 70 square degrees, which will have 1,500 observations, 25 per night, and this is to evaluate templates and such. So I'm not sure well will that get out. How well will that be calibrated, especially at the beginning? But this will be the closest you will get to Kepler or anything like that ever. The LSST will never do that. So you'll have 70 degrees, which will be superbly sampled, and you will get that at the beginning. So I'm thinking about science, which is like Kepler type science, where you're like, at least for variability, looking at the, you know, the slopes of power spectral density and such. But I'm encouraging people to think about that as well, because as you're saying, this is the only time you'll get that kind of cadence.
So let me follow up with that. All of the Kepler AGN variability are thermal instabilities in the spacecraft.
Well, that's an interesting point.
So
we can discuss that.
This will be the further. There are papers.
You will learn so much about the dome of LSST. It's amazing.
Well, I'm hoping we'll actually do science with that,
Right.
and not thermal instability.
And we can discuss, is the precision going to be good enough that you will get anything, especially at the beginning? Yeah, that's a valid question. I
So
agree.
Neven, I mean, there's this document for people to read, but if you could post something in the Slack, you know. if
I
there's-
can post a figure. That's the best I can do.
Yeah.
Okay.
So to go back to your point then, I mean, if you are very unhappy, you are certainly welcome to write up, you know, think it through, write up a thoughtful document, and you're free to send it to the SCOC. Whether they will act upon it or not, well, I'm skeptical at this point because the ship is somewhat sailed. But I'm sure they'll read it and give it due consideration.
I think the only thing that, I mean, Franz can correct me if I'm wrong. I think the only thing that would actually carry weight is if you wrote a metric, got it implemented, and then the simulations were run, and then showing that like here, this whole class of science can't be done with this type of simulations. Like I doubt like a document at this point is going to do it.
Yeah, I agree. It's going to be very hard.
It's
to
probably
move the needle.
100 hours of work to do something like that.
No, I think in that context, it might be also worth considering if, yeah, we're very unlikely to change this, but if there's anything we can complement this with. So you could imagine sort of not so large programs, but with DECAM, for example, at Blanco to try to get that very quick variability on regions being observed of the WFD, right? And so you can build up that missing time frame.
Or you could just try to complement it in the deep drilling fields, so you
Yeah.
wouldn't have to pay so much. You could just fill in whatever weaknesses the deep drilling fields still have. Yeah. Right. We're good with that one. Okay, something on this.
To follow up on that, am I right in saying there's still some scope for micro surveys as well?
Yes, I mean.
So for what? I didn't know.
Micro surveys?
Yes, and there is some discussion of micro surveys. I
And there's
believe on the next.
there's two that were
Yes,
recommended.
there are
right?
two micro surveys. We weren't going to go into them here, but you can read about very briefly. There's going to be a near sun NEO twilight survey.
Sure,
So
so
during
the,
the twilight.
the point is, if you wanted to propose a new micro survey specifically to do high cadence,
Well, yeah.
that could be another option.
Yes. There are a good number of those microsurveys that have already been proposed. There may be still time to do that. I don't know.
I think there'll be calls in the future for
Microsoft
for like second year, because at the beginning, I think Franz must know more.
It says it here.
The problem is you don't want to give too many microservers in the first year because you don't know if the telescope will actually work. But once when you're up and running, there will be more area for that.
And here they say additional microsurveys should be added in the future when the system
Right.
characteristic survey is better assessed. So there may be scope for doing that in the future.
Definitely. Definitely.
Okay. We good with that one. Should we go through? We probably shouldn't go through every single one of
No,
these. We'll
but
pick off the
I mean, do we
important
want
ones.
to say anything about the filter distributions?
Briefly, yeah. So we have to go back to the previous page for the filter distribution. It's here.
I actually think you have to go to the, if you want to actually see it, you have to go to the detailed section.
Yeah.
Because this doesn't say
Okay, you
anything
want-
about the filter distribution.
Okay, so go to section 2.3.
Page 18. It's like. Is there a good figure, Franz, that we should look at?
I don't think so. But there is some text at least that is talking a little bit more. So if you go down one there, so yeah, I mean, I guess this is fine, but basically, I think the filter distribution is slightly blue at this point. And there, I mean, or actually, let's see, yeah, basically skewing the filter distribution bluer would harm several science cases while benefiting only a few. And so like doing lots and lots of U-band, for instance, isn't on the table anymore. That's kind of the main point. So there's a certain filter balance that's in there in terms of number of, you know, GRIZ, and then U is kind of relative to that. The only thing that is sort of still in play is that at the moment, the U band is swapped out with the Z band for some reason. I had always thought it was the U band swapped out with the Y band, but because Y is not very sensitive, I guess they're swapping it out with the Z.
Wait, so
And-
Franz, hold on. Let's make sure everybody understands. Not all 6 filters are available at once. You only get 5 at a time, and 2 has to, you know, they have to be swapped out, right? And that takes what, an hour or something, or
Yeah, I mean, it can be done during the, well, the filter can be done during the day, right? But they basically, during dark time, they have the U-band filter in. And during bright, you know, noontime, they take it out and they put in one of the red filters. And the discussion was what filter should they swap it with, Z or Y, or a combination of both. And that isn't fully decided yet because the supernova metrics for high redshift are not as good as they could be. And one reason is probably that they're swapping out Z, which is so much more sensitive than Y. And so they can't go as deep because they don't have Z in there. And so there's some discussion about basically keeping Z in and just swapping out Y. I don't know that affects us very strongly, but. Yeah.
And if you care about like tidal disruptions, I mean, some of the people that were pushing for a bluer filter balance and more time in U were, for example, the tidal disruption people. So if you care about tidal disruptions, this affects you, and you probably should learn how. Good with
But
that one?
as Roberto said, I mean, you know, for the brighter objects, one could have dedicated programs at a higher cadence or in bluer filters to go over portions of the sky. And then, in fact, several telescopes in Chile are planning on doing something in that order.
wrap up with DDFs?
Sure. And then again, there are some more points. Can we go back to pages 3 to 5 again? There are many more things that could be said, but we don't want to burn lots of time on this because you can read it. We're just hitting the really important ones. I think the deep drilling field
One
is
more down.
on the next page. Yep. I'll just go through this. Gonna have a pointer so I can get my application. So this one, in my opinion, personally, is good news for AGN science. First of all, they have dictated that no less than 5%, with the potential to increase this as high as 7%, of the whole time of the thing, okay, be dedicated to observing 5 pointings as LSST deep drilling fields. And in the current simulations, the DDS will generally reach a 10-year co-added depth 1.3 mags deeper than the co-added depth of a wide fast deep pointing in the same band. And then, of course, as I mentioned this morning also, they have selected the Euclid deep field as the 5th DDF with a footprint of 2 LSST pointings, so 20 square degrees, but each to be observed at half of the 10-year depth. Okay, we're fine with that. And then, in addition, all DDFs be observed for 10 years. That's very good. Okay, and that's one thing we were arguing for in our white paper, as were others. And so we're going to have good coverage for the full 10 years on the deep drilling fields. And for example, for those of you who want to select AGNs based on their variability, go into the longer time scales, get you further up the red noise power spectrum, get you bigger variability so you can find more AGNs. Okay, so that helps. That's good news. And then also for Cosmos specifically, Cosmos field be observed to a full 10-year depth within the first 3 years, okay, and then continue to be observed thereafter at the same rate as the other deep drilling fields. So they're going to hit Cosmos really hard fast at the start to push it down to the full depth. So that can be a good field to be working on very early. Now then, the final point then is the detailed intranight strategy on the DDS is still under design. I could say a lot more about what the AGN science collaboration has proposed, but it has not yet been decided exactly what will the cadence be yet. Go ahead.
I was just going to say, so the current data challenge is actually just Stripe 82 and the XMM LSS. It's not Cosmos. That was an enhanced goal to add Cosmos. And so it may be something, I mean, it's the obvious thing that people would want, you know, in addition to that. And for that reason, it might be useful to think about doing that. But I don't have any plans to do that myself within my group.
Actually, so the project that Tabby will present tomorrow deals a lot with something like that for Cosmos. So you're turning it into a training sample.
And then just very briefly, you know, what we suggested in the most recent 2021 white paper, as was mentioned this morning, is to toggle deep drilling fields on and off for very intensive coverage in a given year or not. Okay, and you bounce around. This deep drilling field gets extra heavy coverage this year, and these other ones only get heavy coverage this year. Okay, and furthermore, then we have suggested that the SCOC consider what's called an accordion cadence. The idea there being, you know, the bellows of an accordion can be not so densely packed at the end, but very densely packed in the middle. And that's the idea. You'd go in a given observing season, observing it not as densely out at the start of the season and the end of the season when the air mass is high, okay? And then as you go in toward the best part of the season when the air mass is low, you pick up the intensity and you make it very intense in the middle. And that gives you, first of all, improved depth for the people who care about the static science. And it also then gives you a very intensive sampling period when you can do the very rapid time domain things like accretion disk reverberation mapping. So that's the thinking there.
So, I mean, to add to that, that also naturally gives you what we would call long seasons. Yeah. So that helps sample your log delta T a little bit better, you know, more on the 10-month time scale or something like that. And it also gives you a few higher mass observations. So that helps with the variability and the GCR.
Yeah, we have pushed for the longest seasons possible. And if you're very busy, you don't have time. In one of the most recent science collaboration, you know, notes from our telecons, we boiled it down to 10 bullet points. These are the 10 things we want, and it's included in that email. So you can look up that email if you want it boiled down as short as possible. What does the AGN-SC want? At least that's what we're saying we want. And any questions on the deep drilling fields, or is that good? Do people have any overall reactions to this cadence stuff so far? Yeah. Are people happy? Or, I mean, again, I think no one's going to be overjoyed because we're competing with other groups, but the goal is at least no one feels, well, this is a disaster for us. I feel it's probably still going to be really good. But
yes, I think the plan is probably we'll stop here to talking about cadence stuff. Let people read this tonight, tomorrow morning, and then maybe see if that invokes some more discussion tomorrow, and we'll move on to talk about project posting. But maybe Neil and I will shut up for a minute and let people think if there's more to talk about today or questions that you want to ask that we can answer to help guide discussion tomorrow.
I just ask one question. Was the accordion cadence ruled out for the wide field? Because an accordion cadence is a bit like a rolling cadence, but let's say a third of a season, flipping back.
It was never considered.
I did actually mention that informally to a few people for the same reasons you've just said, Paulo. It never caught fire. I never had time to push that. I was focused on just making sure the deep drilling field didn't get screwed up.
Oh, okay.
Basically, it was never put into a simulation, and that's kind of the problem. So it still could be, but as Neil said, the ship is largely rolled on the rolling cadence or sailed, and so yeah.
Yep.
But I think there still is some scope to do that within the rolling that exists to kind of extend the seasons.
Okay. Yeah.
Yeah, so just a question for Franz. I think is there a time scale on which, if people had any suggestion, would it be most useful for the SCLC to receive?
Yesterday.
Yesterday.
Last year.
Probably a year ago. But you know, and again, they did just over the past couple of months say, if you have any more input, do it. I sent one in. Who else sent one in? Okay, well, there you go.
The only AGN person that sent one.
The only AGN person, of course, many other science collaborators.
I guess the flip side to that, Neil, is I didn't consider sending something in because I read the document and thought, well, everything that seems fixed seems fairly sensible, and everything that's still up to debate is second order fiddling around, which I don't really think is worth worrying about from our point of view. But other people might disagree.
Yeah, I mean, I will say there's a few things I'm not happy about, but like 10 years ago, when people were knocking on my door saying, like, you know, what do you want for AGNs and LSST? I'm like, I'm keeping my mouth shut because it's so much less than what's actually happening, right? I don't want anybody to realize, like, you just the default I would be ecstatic with, right? So, you know, like, could I be happier? Sure, right? But
I think we'll be all right. Yeah.
So just to be clear, if the committee says that this is what LS is going to do over the 10 years, it completely set in stone. So later, meanwhile, LS is operating, people bring up a very important urgent issue. If we keep cadence like this, we're going to be in a deep trouble in the same side. Will they consider this as the modifications or?
Well, Franz should address that. I would add to that we may also find that the telescope has all sorts of unexpected problems that we don't know about yet.
Yeah. Okay.
And what will we do then? Well, then reality will force us to change things. But Franz can address your point.
Yeah,
I don't know.
There's multiple things here, but the SCLC will be a standing committee that will exist for the entirety of the survey. It will change composition every couple of years. So it's there exactly to evaluate what's going on and try and pivot under certain circumstances to, again, try and derive the best science with the instrument that you have, right? So commissioning will be one pivotal point where we make decisions that are sort of crystallized in the first several years. And then once we actually start to get data, we might figure that you know, there are some problems and people might have to come up with fixes. And that may trickle down into, you know, other things that are forced to happen. And again, yeah, someone may come along and say, oh, you know, well, if we tweak this, we can, you know, optimize, you know, X, Y, and Z. You know, I think people are happy to be open to that possibility, but it's a lot of work. So, yeah.
So that's there you go. That's from someone who's on the committee. That's most anyone knows. Okay.
How do the other science collaborations feel about the accordion cadence, like Spring Award?
I haven't heard any enormous complaints. I spoke to some people in the dark energy science collaboration they were generally supportive. I mean, one of the big
Because
problems.
they want long seasons.
They want, yeah, well, certainly, yeah, the long seasons part, but the accordance specifically, yeah, is some people were unhappy previously was that the deep drilling fields weren't actually all that deep, because so much time was being spent at high air masses that you didn't actually get a great depth improvement. And so the accordion cadence fixes that, and that made the dark energy science collaboration people happier, at least the ones I spoke to. I don't recall anyone else. I don't recall any other reactions to the time domain science on the deep drilling fields, specifically regarding accordion cadence. I haven't heard any complaints. And it will, I mean, again, it will give you much more dense time sampling and part. It's not going to give you every 15 seconds, but it'll get you I think in the dense part, you're going for like every other day. And that's pretty good. Yeah. And actually, you could get down to every day in parts of it. Yeah. Okay. So that's that. So do you want to talk about, you guys want to
Project
talk?
stuff?
I guess you're.
Why don't you introduce it for 10 minutes, and even if you can't demo it,
Sure.
Maybe you give people the links that they need for the Slack in case it's back up tonight, and then we can talk about it more tomorrow.
Sure, that sounds good.
Great.
Right. Yep.
Actually, I don't have anything to present. Just in case it comes back.
It makes you more
alive.
comfortable to have a laptop.
Yeah. Yeah. So, well, with Chris, we've been actually working on setting up a project tracking system, right? And a big part of the trying to motivate more things going on, more collaboration ongoing, is that we kind of need to know what people are, what we're working on. And so the idea of the project tracking is so people can put out the actual projects that they are developing, so you can see how it compares to what other people are doing, what are the synergies, what are the competitions, and that way you can actually start building up using the depth of the collaboration, right, to start building up your project. So it took a while to finally decide on a system, but Chris actually brought the idea of using Open Project. It's actually a very simple open source tool that actually the free version, it's actually not open source, I think. Well, I'm not sure. I think it's open source actually, but the point being that it's actually the free version of it has enough things for us, so enough properties for us to actually do pretty effective project tracking. I would show you what it looks like. Last night, we actually had a massive power failure at the university, and it's actually not running right now. So hopefully, I did ask somebody to go to let me know as soon as they could turn it back on, but currently it is off. So what is the idea? So actually, when you log in to this, actually you can see a list of all of the projects that actually have been submitted. But so far, so even though it's ready to be used, the main holdup right now is that we need a publications committee, right? And that the idea of the publications committee in this case is that if you want to post a project, you would submit it to the publications committee through a Google form, as Niel mentioned. And the idea of that is the publications committee can say, yeah, this is an appropriate project to post, right? And a big part of that is not trying to cordon off science. If you want to say, my project is to study TDEs in the 5th year of LSST, that's not really a project happening right now, so that's not something you should be cordoning off. But it's a kind of a very quick, easy check, but the publications committee should decide what it is actually, what are those boundaries, and also what kind of categories you want to put things in. So for example, you could have projects, but also ideas, things that people are thinking that the collaboration should do, but they're not actually actively doing. And we can also use this system to post all of that. But I think that's primarily the holdup right now. I don't know if you want to add anything, Chris.
I mean, one of the things why I decided to get involved in this was when I joined a little over a year ago. I heard Gordon saying, hey, we have all this work, we need people to do this work. And I kept thinking, as someone like completely new coming back to LSST, well, what is there? Like, there's so much information when you join. Initially, all the documents to read through and stuff. That this is why I thought it'd be really good, because if I'm feeling this way, then other junior people probably are too. So one of the cool things that we can use this in this project, the open project, is that we were thinking about if someone posts a project, you can have a flag that says like open for collaboration, right? So if there are people out there that are looking for projects or want to get involved, don't know how, and they see something and they're really interested, or it's something they have some experience with, or they have the time, and it's, these things are open for collaboration, you can then message, the administrator or the leader of this project and say, hey, like I have some time, or I've done this, or I would like to do this, or I would like to get the experience doing this. And then hopefully most projects would be open for collaboration, because our collaboration, but and so that's like one of the things.
I guess I would say if you're not open for collaboration, then you are basically trying to cordon it off.
Yeah.
Yeah. So
yeah. Without really being able to show it. I mean, I guess we could go to the website and just show, like, that's probably not. What's really cool about this is that, how about a show of hands if anybody's ever seen a project or like software management, like project management software before?
You mean like Jira?
Yeah, like for those who haven't, it's it's really cool. Like there, you submit that you have this project and it's got all the different tasks. You can set up as much, or as little as you want, like different milestones, different things that need to happen, so that you can really, the more you put into this, the more the rest of us, looking at your project will know what needs to be done. So one of the things that we're doing also is trying to come up with the guidelines for like how you set up a project, like what should be kind of the baseline when you submit for a project, like what it details.
What do we have the specific details to which degree people have to specify the project as a good one that actually open for the collaboration? I mean, it could be a various range of ideas. Some idea could be very mature, but some ideas may not be very mature.
Right.
I mean, is that the job actually the publication committee decided which projects should be worthwhile to post it in the system?
Yeah. And one of the things that we've had discussions about is, potentially someone has a really good idea, but they need help, or they want to see if there's other people out there that want to collaborate on a very specific project. Then perhaps you can submit it, and there's different tags, right? Like this is something that's a concept, or I'm soliciting feedback, or this is work that's already ongoing, and now I'm publishing this as a project, things like that. And so that will really come down to the publications committee, I think, and how we set up this Google form.
Sorry, it's not that I don't want to be rude. I'm actually talking with the IT person at the university to see if he can bring it up.
Is it worth me posting the user's guide that you sent, or is that?
That's still not full, but I think that might be a part. So that'd be useful. Certainly. Right, we're still waiting for it. Sorry. But yeah, so in terms of very practical terms, so how this works, actually, you get to the web page itself, and you can create an account on it, and you just request to create an account, and then it goes currently to Chris and me to go and approve your account, but eventually that will go to the publications committee, or anybody that can just check that you're actually part of the AGN science collaboration. So then you can go into the project list and actually just start looking at the projects. Currently, you will see something very simple. There's only a couple of projects that we've been thinking with Chris that we put as test projects. And then there's one already published paper from Angelica Kovacevic, which she did the whole sort of put it as a whole project and show like towards the end, so clicked all of the boxes, and then finally the published paper and the link to the published paper. Right, it's ideally how all of these projects will end. That's the ideal.
How are you gonna deal with people with different data rights?
Right, so that is something that we need to figure out exactly how to do. But in the end, really, so this is the way it's set up. You, when you declare the project, you say whether you're open for collaboration or not, and whether people need data rights to collaborate. And so the way it's set up, actually, there's a little box that currently on the crease, right, can click for every person that says you have data rights. So then when you actually add people to your project, you immediately see a little box that says this person has data rights or not. Now, cross-matching that's probably the more difficult part because that needs to actually be up to date because people will be moving in and out of data rights. And I don't know exactly how the best way to manage that is, but other than actually having every 6 months somebody go and check, compare the list.
I mean, this is only critical if you're passing actual, low-level data to your collaborators. If you're passing like higher-level derived products, then there's not really much of an issue.
Okay.
Like, so no images, for instance, no magnitudes, but if you, have a plot of colors or something like that, then maybe, I'm not even sure colors may be an issue, but, derived products, star formation rates or stellar masses, that might be completely fine to pass along as a table to your collaborators, for instance.
Right, but if you put like a set of targets with colors as a table, then that you can't have anybody in your paper that doesn't have data rights.
Well, I think once you publish it, it's fine. It's just the passing of the data. You need to read the exact rules, and I think there are versions of them that are floating around that change with time. But yeah, in effect, there are certain levels of products that you're not allowed to pass along, but those might all just be on the the LSST server, and you never take them off of the LSST server. And so then maybe you make a plot of them, but the plot isn't going to have individual sources, right? So in effect, it's not, you can't recreate the information, the original information. That's the main point, is that you shouldn't be able to recreate the initial raw data that LSST is producing for data rights holders.
Okay, so if I understand correctly, the idea is that there's no issue with people without data rights being co-authors in papers that use data. It's them being able to get their hands on the data specifically.
That's my understanding is.
Okay. All right, so that actually helps a lot.
You could mention Rachel Street's data rights management system.
I understood that was not going to happen.
Oh, that one wasn't funded? Okay.
I thought so.
Okay, maybe it wasn't funded.
I think
there was an attempt. Okay.
Yeah, so there was an attempt to actually produce an actually integrated system for memberships and to make it easy to happen. But I think it wasn't funded because LSST is looking themselves to do this. That's what I understood. But how it's going to work, there's still very, there's a few options, and at least one of them is easily interfaceable with this tool, such that we could actually hand all of the membership to that system through LDAP.
So I think we're at time, and hopefully I've given people enough to think about, and we can continue discussions tomorrow.
Yeah, so hopefully by tonight that link that Gordon sent will be up. Everybody should be able to create accounts. Currently it's actually running on a test server that will migrate to a final server once it arrives. So we're in the process of buying it. We hosted at UDP. So hopefully it won't crash if everybody tries to create an account at the same time. But that's that's all. You will see the Google form to submit things, but don't use it because nobody will actually check that. So there will not be any projects added at this moment.
Well, again, I'd like to thank both of you for putting in the efforts on this. It's very helpful.
Oh, yeah.
Session. We will start with the talk by Drexel.
who is going to talk about expectations of time delay measurements in electric galactic nuclei with the Vera Rubin Observatory. So I will do
You want me to go over slide for you?
Okay.
You tell me when should
okay,
I?
I can.
But that should work.
This is.
Yeah, this is four. Okay. Yes, sir.
Okay. So good afternoon, everyone, and I'd like to thank organizers for giving me opportunity to present our work here. So I'm here on behalf of my group. So I'm going to talk about the work that we are doing for LSST AGN Science Collaboration, and we are participating as an in-kind contributor, and we are developing a software to measure the emission line time lag from the quasars that will be observed from the LSST from both main survey and DDF. Okay. So this is like the main objective, and basically we are planning to measure the emission line time delay from the quasars. And this is kind of the summary that we are developing a tool that can measure the emission line time delay from the thousands of quasars that will be detected from the LSST. And we have implemented the recent cadence that we have and in our code, which is kind of very useful to put a better constraint on the lag value. And since currently we do not have the observational data, so we are kind of simulating the AGN light curves and then using them for the measurement. Okay. So basically, why we are interested in LSST for measuring the emission line time lag? Basically, our main objective is to do the cosmology using quasars. So why we are interested in doing this is because of this Hubble tension. So here I show the cosmic evolution of our universe. So we know that from the Planck collaboration, from the CMB measurement, we have the H0 value around 67.36. And there have been like a recent development where people are trying to measure the H0 using the local measurement in the local universe. And one of the best results currently we have from the supernova one from the source team, and where they measured this H0 around 73.30. So now what this kind of suggests is basically so this 67.36 comes from assuming the standard lambda CDM cosmology, which kind of suggests that the cosmological model that holds here doesn't hold in the local universe. So if you want to explain our local universe, we need a different cosmological model. Other thing we can do is basically we can look for the we can basically test this value by using the different independent measurement and try to see if we are getting the similar result or different result. Okay, so here I'm like showing a plot from this Valentino et al. 2021, where they summarize the recent measurement that has been done to measure the H0 in the local universe. And on this side, we have from the CMB measurement. As you see that from the local universe, in most of the methodology, we have the error bars quite high, and some of the cases kind of process the both part, and we don't know exactly if this measurement can be reliably used or not. On the other hand, we have for the supernova, we have like proper like good measurement, but then we also have the supernova, which is like calibrated from the tip of the red giant branch here, which kind of basically suggests that if you are using the same source and if you are calibrating it differently, you are getting the different results, which kind of motivates us to choose the independent method to do the cosmology. And we think that the quasars are important here because they are very bright, and also they cover the very quite large redshift range. So how we are going to use the quasars for cosmology purpose is basically using the BLR reverberation. So I will just tell you about what is reverberation. So we know from the EST observation now that every galaxy has a supermassive black hole, and if the galaxy is rich in the gas, it can accrete the matter, and it form an accretion disk. And this accretion disk emits mostly in the optical and UV, and this emission we call as a continuum emission. And then this continuum emission can photoionize the BLR cloud. We don't know exactly like how the clouds are produced, this BLR cloud, and what is the structure.
And but this continuum emission can photoanalyze those light and produce the emission lines. And these emission lines follows the variability pattern as the continuum, but it will be like very smooth and it will be shifted in time. And the time will be corresponding to this light crossing time between the accretion disk and the broadline region. Now, from the photoionization theory, it suggests that if you cross correlate these two light curve, you measure this time lag. And from the photoionization theory, it suggests that this time lag correspond to the something called the radius of the broadline region, which I mentioned here, RBLR, and it will be proportional to the luminosity of the source power half. And so if you do this reverberation for more and more number of sources, you can end up with this kind of relation. This is from the Bench et al. 2013, where they have measured the radius velocity. So this is called the radius velocity relation. And they have measured for the H beta sources, and they derived this slope around 0.533 and this dispersion around 0.19. So it suggests that if you do the reverberation for more and more number of sources, we can standardize this relation, where the alpha and beta are the three parameter. We can measure it from the radius velocity relation, or we can also measure it from the theoretical prediction. Like if you have the very good model that can produce that can tell you about the structure and size of the broadline region, you can exactly measure the alpha and beta. But since currently we do not have any realistic model for the broadline region, so we can rely on this emission line measurement and this radius velocity relation. So our goal is basically to standardize this relation and measuring the value of alpha and beta, and then further we can use this relation for measuring the distance of the sources. So this is from the our work. So this is So we are doing basically monitoring some few of the bright and high redshift sources that I show here too, and there is one source here from the SALT telescope in South Africa, and we are measuring basically the MG2 emission line and trying to standardize this radius velocity relation. And this is from the archival data from the Humayuni et al. 2021. And from there, we can standardize this radius velocity relation for MG2 also. So why I'm telling you this? Because we can have this radius velocity relation for different species like H beta, MG2, and carbon 4. And then we can combine them together to have some relation, something like this. Okay, so I forgot to mention here. Oh, sorry. Yeah. So how we are using this radius velocity relation to estimate the distance. So basically, once you standardize this relation, you already know the alpha and beta. And if you know the alpha and beta and everything, then you can pick any source and measure the time lag. And using this alpha beta from the standardization and the time lag, you can estimate the luminosity of the source. And then you can have estimate the luminosity distance. And from the spectroscopic observation, you can know the redshift of the source. So you can basically finally derive this luminosity versus redshift relations. So here we have combined the result from the H beta, magnesium 2, and the carbon 4. So it goes around let's say 3.5. And then we use the different cosmological model to fit it. And then we have this value for H0 68, and then for omega m around 0.295, which is kind of mostly consistent with what CMB says. So from the current result, we don't see any tension in the H0 value. But here the thing is currently we have very less number of reverberation mapped sources. So you see in carbon 4 we have around 40, and then MG2 around 90, and then around 120 in H beta. So with LSST we are trying to we know that the LSST will observe large number of sources, so we can have reverberation mapping from all those sources, so we can extend this relation and we can have more number of sources on this plot basically. So okay, so you must be wondering LSST is doing basically photometric observations, so how we are going to do the emission line time lag measurement. So basically here I show the LSST filters in the background. On the top of that we are plotting the quasars composite spectra, and based on the redshift of the source you can know which emission line will fall in which filters, and you can pick those filters, and you also know that in which filter you will have the continuum emission. So you can subtract this continuum emission from that particular filter, in this case, let's say in this case, and then you have the purely line emission, and then you can cross correlate those two filter to measure the line. So in our simulation, what we are doing basically, so there would be like some redshift where this emission line would fall like something in the edge of the two filters. So this kind of redshift we didn't choose in our simulation. So we had to restrict our filter range, like I mentioned here, for the G, R, I, and G band, and we are choosing only this for filter because here you see their efficiency is quite high compared to these other two filters. And in our simulation, then we are also choosing the broad emission line like H beta, Mg2, and carbon 4. And because we know the radiation velocity relation for those sources. And then we also, yeah, so depending on the redshift of the source, you can also have this kind of situation where for a similar redshift, you can measure the two emission lines rather than one. Okay. So first we kind of try to do simulate the spectra of a AGN. So for that, of course, we, as I mentioned, we use this all these emission lines, and then we also have the Paula continuum. And then we, with the Mg2, we know that it also comes with the Fe2 emission. So we also add the Fe2 emission combined with the total like continuum Paula and then other H beta, Mg2, and carbon 4. Okay, so in the next, what we do is basically we simulate the artificial light curve. So for that, we are using this Timmer and Koenig methodology. And for that, we are choosing the broken Paula PhD. And then we also simulate the dense line emission light curve, where this information goes. Like we have to provide some time delay because we have to shift that light curve with that time delay. And this time delay that we are choosing is like physically motivated from this Lorena-Cheney's model for the broadline lesion. And then we are using this, and then we use this LSST cadence basically to, so we have the light curve, so we have the LSST cadence, so we kind of convolve those information together to have a pure light curve like this. So we have R band light curve and I band light curve. And then we can, and then we have this convolution also with the cadence. And then we can basically use, we can use those light curves to estimate the light. Yeah. So some of the parameters, because there are a lot of free parameters. So these are the all the parameters that goes into our model. So some of the parameters we have chosen it from the this SDSS DR14 Quasars catalog. So we have like the luminosity and then equivalent width for all these three emission lines and also the FWHM that we have taken from this median value of the distribution. Okay, so this is the kind of result that we expect from the main survey. So as you see, so this is so we have divided this whole sample in the low luminosity and the high luminosity, so like faint and bright AGN, which is luminosity around 44.7 for faint and 45.7 around for bright AGN. So for the faint AGN, we see that for the main survey, we are not able to so these are the black points are basically what we provide to the simulation, and these are basically the recovered data points. And the error bar on this recovered data points comes from the Monte Carlo simulation we do like 100 to 1000 times on each leg. So as we see that for the main survey, the till redshift 2.5 it is not kind of recovering the lag for all these sources, but like after 2.5 we have some so we have some sources where the time lag can be recovered. Now for bright AGN, we see that it can cover, the main survey can work for like redshift 0.5 to till redshift 3.0, and then we can have proper time lag recovery from the main survey itself. Now from the deep drilling field, since we have like different, we have like 3 and 4 different deep drilling fields, so we are choosing like for our simulation one deep drilling field, and we know that from the in the each deep drilling field how much the number of visits will be there. So this number of visit also includes, like as we as they were discussing in the previous talk, like we have like in like 1 second measurement kind of like thing. In one day you will have many number of measurement. So for our reverberation mapping, like those kind of measurements are not relevant because we are looking for a longer time delay. So we kind of divided our cadence in like one data points per day, and with that we have like this number of visit over a 10 years. And then we also have this seasonal gap. So this is like I'm showing plot for the first year of operation. So we will have like around 6 months of seasonal gap in the data. And this is the histogram for the time separation that we can have from over the 10 years for these two R and I band, because this R and I band has like more number of visits from the LSST. Yeah, so this is the result from the deep drilling field. So from the deep drilling field, we see that from the till redshift, like after redshift 1.5, we can have a good measurement from the LSST. Because for the main survey, we saw that till redshift 3, there was no proper time lag recovery. But for the deep drilling field, for the faint AGN, we still have like till redshift after redshift 1.5, we can have a good recovery of time lag. And for the bright AGN, there is not much improvement compared to the main survey because it is also able to recover the time lag till 6.5 to 3. Okay, so since we already have the models, we were thinking, okay, the data is will start coming. So we wanted to test like using the first or second year of data and try to see if we are going in the correct direction or not. So this is the result from the first year of like after the first year from the LSST, and this is the after 2 years of observation from LSST. So we see that for the faint AGNs, like at high redshift, it's not able to, we are not having like a good recovery of the time lag, but only the low redshift sources can recover very well. And for the bright AGN, we don't have like, they are like very much different. And after 2 years for the faint AGN, we can have the proper recovery from the redshift 0.5 to 3. But for the bright AGN, we still don't see like after 2 years, we'll have a proper recovery. We'll not have a proper recovery of time lag. So then we also, since in our more simulation, we already had like many parameters. So we also wanted to test the sensitivity of our result using the different changing the different parameter and try to see if the result is varying or not. So for the equivalent width of H beta, earlier we assumed like around 150 angstrom. So currently we choose this value from the SDSS around 67 angstrom and try to see if we kind of recovered the time lag properly or not. So this is for the redshift 1 for the 10 years of observation for the so this is for the first year of observation from the DDM, and we see that we are like able to recover the time lag properly till redshift 1. And this is the choosing the error bar and the photometric accuracy from 0.001 to like we have increased it like 0.02 and try to see if it is helping to recover the time lag. And we saw that here we are kind of able to recover the time lag for both faint and bright AGN. And then then we also have this Quasar's variability, and so we kind of like change the Quasar variability and reduce the Quasar variability and try to see if it affects the result. So we don't see any much effect on the lag recovery. And but then we also have this PSD that we are using to simulate the light curve. So we change the low and high frequency break and try to see the if it is kind of recovered the lag. So here I show the result. Yeah. So we have here till redshift 1. So basically, we in all these 3 cases, we kind of able to recover the time lag properly. Okay. So in the other test that we did is basically earlier when we were simulating the light curves and measuring the time lag, we are assuming the radius mass relation same for all the emission lines. But now when we choose the different different radius mass relation that is derived from the observation, we have the recovery lag, which is kind of I mean, there is not much improvement, but we have proper recovery lag after let's say 0.5. But in this range, we are not able to recover the time lag properly. And so this is like the part of the H beta. So there is some issue with that beta measurement. So somehow we are not able to recover the proper time lag. Yeah. So. Yeah, so the next thing is basically assuming the BLR response. So currently, I mean, in the previous simulation, we are using the symmetric Gaussian profile as a BLR response to estimate the, to account for the BLR response to the emission lines. Now in the current plot, we are using basically the half Gaussian that is also been suggested from the observational data in Keith Horn et al. 2021 paper. And with this, we are also like able to recover the proper time lag till let's say 3. And then we also try to see using the different cadence that has been proposed earlier. So we had like different cadence in main survey and the deep drilling field. And then we have this separation, effective separation, and then this offset time delay. So the offset time delay is derived, estimated using this expression. It's like the ratio of derived by adopted time lag. And so here I plot basically this survey cadence, and then we have the redshift on x-axis. And we try to see, and the colors are basically the ratio that we have from the derived to adopted time lag. And we try to see like which cadence is best, and it can like which cadence provide the better result over the redshift range. So here we see for the Penn AGN, it's like after 1.7, we have like better measurement for like all the cadence, and in the bright AGN also we have like after redshift 1.7 we have good recovery time lag. And in some of the cases like this MS6 and MS7, we have the recovery lag for whole the redshift range. And similarly in the bright AGN, this MS6 kind of recovered the proper time lag for whole redshift range. So basically this kind of helps us to also choose like which cadence is better for the reverberation. So this is the summary. So basically the LSST will provide, of course, not millions, but let's say hundreds of thousands of sources that can be used for the cosmological purpose or for the measuring the emission line time delay. And in our simulation, we estimate the like possible result from the 10 years of LSST observation, and also tested the first and 2 years of observation. And during the first year, only the shortest time delay can be measured, and which means that only DDF are useful for this purpose. And the DDF data will allow a measurement of time lag of bright AGN, and for most AGN and most and even faint AGN at redshift above 1.7. And the like large number of measurement can reduce the statistical error by 30%, and almost approach an accuracy of 1% in distance measurement. And for the main survey, only bright quasars will have a delay measurement. I mean, because in the main survey we'll have a like more number of sources compared to the deep drilling field. So even though if you are measuring the all the bright sources, we still have a very high large number, and it can help to reduce the statistical error in the time in the cosmological measurement or in the distance measurement. And we saw that the possibility of measuring the time delay mostly depend on the source luminosity and redshift, and not as much on the actual cadence. So the other thing is basically in the current simulation, we assume the luminosity and the redshift of quasars, but in reality, the LSST will observe many faint AGN that we don't know the redshift of the sources. So this information we have to keep in mind. And okay, so in future we also plan to include the disk reverberation part in the BLR and try to see if it improves to measure the H0. And for the disk delay, of course, we already have this paper that one can look at, where they have already tested the the feasibility of deep drilling field estimating the disk emission time. So yeah, thank you for your attention.
So this is really interesting. So I assume you would need at least one spectrum per source because you need to know the redshift.
Yeah, so currently we are relying on the photometric redshift. So I mean, of course, if you have the spectroscopy, of course, you'll have better measurement of the redshift. So we can have a follow-up measurement, but I don't know it will be possible to have follow-up measurement for those huge number of sources.
Okay, okay, but when you are considering the uncertainties, that is considering the error in photometric redshift.
Yeah.
Okay.
Photometric redshift.
What happens at 1.7? Is it one of the important lines falls out of the filter that has a strong relevance to your method?
I don't think it has any problem, relevant thing here like redshift 1.7. It's just that somehow we see after redshift 1.7 the lag recovery is good in main survey and in the DDF as well. But from the line perspective, I'm not sure.
Have you thought about trying to test your pipeline with CTF data before LSST comes online?
Okay, we have not used on the GTF data, but of course we plan to do it, yes.
No, let's back again. Sorry, I will not be able to pronounce your name. Okay. So next speaker is Chris Uberlach, and he's going to talk about revealing changing loop quasar candidates in SDSS state 82 with SDSS, PANSTAR, CTF, and LSST data.
Yeah, or just about changing the quasars as soon as we get the slide.
So I will let you know in a few minutes.
Okay. Okay. Are we good? Okay. Hi, my name is Chris Uberlach. I'm a postdoc at the University of Washington, but I did my graduate work working on quasar variability. So this presentation is going to concern changing loop quasars, and in particular, what sort of interesting things can we discover when we compare damped random walk parameters from different surveys. So first, a quick primer on quasars being variable sources. What does their light curve look like? I skip all the pretty artist impressions because it's an AGN conference, so I don't need to convince you that quasars and AGN are interesting. But just to show the spectroscopy people the light curve, most of the time it's very sparse. Okay, there it is. This one. Oh, okay. So maybe I can just point with this. So most of the people are used to the fact that quasars are variable at about 0.2 magnitude level over 1 year, and a good mathematical description, not necessarily correct, but nevertheless a description of that behavior is a damped random walk model, which is characterized by two parameters. That's what makes it appealing to many people. Only asymptotic amplitude, which is a measure of how much your object varies, and characteristic timescale, which is the measure of the decorrelation timescale. And I'm going to show you an example of what this means. So first, if you simulate objects with exactly the same amplitude, but you change timescale, you notice that for a shorter timescale, the points vary much more rapidly. You can see that they decorrelate much faster. So that points that are separated by more than 50 days are not correlated with each other. And then the more you increase the time scale, the smoother the light curve appears over exactly the same baseline. So that's what we mean by time scale. And the other parameter, asymptotic amplitude, you could simply think of this as the amplitude of your variability. The y-axis here is exactly the same. For fixed time scale, as I increase the asymptotic magnitude, the asymptotic amplitude of variability, the magnitude by which your objects vary changes. And those two parameters are useful enough for two purposes. In fact, any parametric description of quasar variability is useful for those two purposes. For either classification, and there's already been talk about that today, when it comes to distinguishing, say, quasars from stars, quasars from galaxies. And the other application is estimation of physical properties. And that's when we're trying to figure out what is the connection between your variability parameters. Could be Damtran-Moog parameters, but could be your favorite karma model, could be any other parametric description of quasar variability, and connect that to known properties from based on spectroscopy, most likely black hole mass, luminosity, Eddington luminosity, stuff like that. So things that you usually have to derive from a spectrum, which is very expensive. So once you figure out this connection between variability properties and your spectrum derived properties, then you might be able to say a little bit, at least, about those millions of quasars for which you will never have time to get a spectrum for. So that's why it is a very important utility of any sort of parametric description. For classification, it was already shown today. I think Paula had in her plot, presentation, a very nice plot showing that galaxies and stars have a very different Damtran-Moog value than quasars. And it was so different, you didn't really have to ask a question, are we off by 10 or 20% when we're describing the Damtran-Moog parameter for quasars? So as long as the two classes have very distinct values, you don't really care about biases too much. But when you're trying to estimate physical properties, then biases are important, because then you might be under or overestimating the derived black hole masses or luminosities or anything like that. So then how can we improve the retrieval of Damtran-Moog parameters if we are trying to peg those Damtran-Moog parameters to physical properties of quasars? Szyman-Kozłowski, and we have proved that he was correct. He has shown that extending a light curve baseline is the best bet to improve your Damtran-Moog parameter recovery. And we repeat this Gedanken experiment at simulating light curves of exactly the same baseline, but injecting different timescales. So as I showed you earlier, it would be light curves that have either a very, very smooth light curve or very quickly varying light curve at exactly the same SDSS baseline. And we do that for each of those values of ratio of timescale to baseline. That's what we mean by raw input on this x-axis. And y is the fitted value. So what sort of timescale do we recover from that simulated light curve, and do it 10,000 times for each value of rho? What we find is that there is a region where your light curve is long enough compared to the input timescale that you are able to recover the input timescale. So that means that you're not biased in any way. That's the well-fitted region. But then if your light curve is too short compared to the timescale you're fitting, then your result starts to be either biased or in the worst case meaningless, because at some point you're just hitting a flat part. So your light curve is simply not probing enough timescales to be able to recover that input timescale correctly. So that's important for just quantifying how how correct is your retrieved timescale compared to the length of the light curve? And also, what can you do to improve? So the best thing that you can do if you have a light curve that's perhaps here, you are fitting a timescale of 600 days for a light curve that's 600 days long, then you're not getting a correct result. Your best bet would be to extend this light curve 10 times. So it's a 6,000 days light curve. Then if you're fitting your timescale, then you're at this point right here, where your baseline is 10 times larger than the timescale that you're recovering. So that's what we did in our study. Okay. We took SDSS data, added PS1 data, also added in some part simulated LSST data. We considered adding CRTS, PTF, and ZTF data as well, just to be able to bring in as much data as possible to extend the baseline of the light curve. Very quickly, LSST is going to bring us this legacy survey data, and then in my view, that's going to be one of the quickest papers that you can write from the first few months of data. Just combine that with that. Treat the data of LSST in conjunction with all the other surveys. So that's why all these quick cross-matching tools are so important. There. In this particular experiment, we took SDSS data and PS1, decided to ignore ZTF and PTF simply because for most of the Stripe 82 spectroscopically confirmed quasars, they were so faint that the error bars were too large and we were getting too much noise in the retrieval. And PTF, ZTF, R-band filter requires some sort of photometric color transformation to bring it into SDSS-R. Whereas PS1 R-band is very, very similar to SDSS. It's less than 1% offset across a range of magnitude. So that's why we're comparing only SDSS to PS1. And what we find is that for majority of quasars, the damped random walk parameters based on SDSS compared to those from SDSS plus PS1 are very similar. There are some that are outliers in the upper right hand side of the corner, both in terms of timescale and in terms of amplitude. The first thing that we did was to take these global parameters and compare them to all the physical properties, just like Chelsea did in her 10 years before paper. And we confirm all the results that she found, because the results were not that much different for the majority of quasars. The amplitude of variability still being anti-correlated with bolometric luminosity. The gradients here are similar because we are trying to show that what we observe here, this gradient in amplitude that goes across absolute luminosity and black hole mass, is what can be recovered from simulation. This is paper by, I think, Kubota 2018. And it shows you that as you decrease the accretion rate, you increase variability. You increase the variability amplitude. That's what this red color stands for. And that's exactly what we are observing here. The amplitude is greater for those sources in that corner of the black hole mass versus absolute luminosity plot. And it's very similar to the gradient shown by Chelsea McLeod 10 years before. We can combine the two parameters into Eddington ratio, because that links both the bolometric luminosity and the black hole mass. Since we see the gradient, maybe we can turn that gradient into a slope by combining the two parameters. And indeed, very similar finding. Her fit was the pink line, our fit is the orange line. The two still agree that lower Eddington ratio would correspond to decreasing fuel supply, perhaps larger variability at smaller Eddington ratios. Finally, it was mentioned before that there are those outliers, and we looked at those light curves in more detail and see what are those objects, what do they look like. And it turned out that when you compare those parameters between SDSS and PS1, you find objects that really vary by quite a bit more than 0.2 magnitude RMS between SDSS and PS1. And as I have showed you before, the SDSS and PS1 filters are the same. So it's not a question of those objects, being off by a photometric color difference. Turned out that perhaps these objects really are member of this class of quasars that they came to be known as changing look quasars, the changing look phenomenon, which strictly speaking corresponds to the disappearance of the broad emission lines. So here for illustration, that's from Chelsea 2019 paper, where you compare SDSS and MMT spectra, and you can see that not only continuum level changes, but also the line width changes as well. In some objects, one of the lines disappears, like here, very strong line, and here it's almost down to 0. So those objects undergo really interesting transitions from perhaps type 1.8 all the way to type 1, or all the intermediate types that are all based on line ratios. So we have proposed the list of all the candidates that fit in the red box. Of course, you can extend the box, and I looked at that too. It might be that our changing look quasars are just the tail end of a continuous distribution of changing look variability. So it's kind of artificial to say that, it's like a special group. It's just that they vary, and some vary little, some vary more and more and more until you hit the tail end of the distribution. One of our candidates already has been reobserved in 2019 and has been confirmed. It's this one. It was picked up in that list of 40 candidates. You can see change from roughly 20, and here it goes up to 19.2 and goes down to 21 during PS1 time. And it has been confirmed by these additional observations. So I suggested spectroscopic follow-up of those changing look quasars using a 3.5 meter telescope at Apache Point Observatory. SDSS telescope is this one, it's on the same mountaintop. And first, I show you a preview of those, what sort of objects I was looking at. That's from Young 2018. One of the objects that we followed up was already observed twice in 2005, 2008 with SDSS. And some studies just look at those two spectral epochs to be able to find objects that change their spectral properties from epoch 1 to 3. But many objects do not have as many spectral epochs, so that's why this variability-based method at finding those interesting objects is still interesting in its own right. So this is one of the objects that we followed up. And indeed, you can see the two SDSS levels in yellow and green. And APO seems to be coming back to the level from 2005. So it was 2005, it was here, then it came up, and here it's down again. The next level is of course to fit the widths of all those lines, H alpha, H beta, and compare directly what are the equivalent widths and what's the difference. That's another example of a quasar that was picked up by Young 2018, comparing the two epochs between 2001, 2008. In the difference between the two SDSS spectra, you can see how H alpha shows you a huge difference between the 2001 and 2008 epoch. And that's another one where we find that from APO spectrum from April this year, that there is indeed a difference. And next step, of course, will be to quantify that. Another object that we followed up, here 2000, 2001, it went down, and here it appears to have a much stronger continuum than it had before. So all those objects have very interesting changes. That's an object from S82 that only had one epoch and it has not been followed up in any other paper. So here is the spectrum in 2023 this year. And again, you see that it is brighter because the continuum level is slightly different. So it's interesting to see that indeed the levels that you detect from photometry, which after all is like broadband spectroscopy, are reflected in spectroscopy, and spectroscopy gives you a more detailed picture of what's going on, so that you can use variability as this tool to select the follow-up candidates. That's another example where you had a turn off, complete disappearance of H data between this epoch and that epoch. And we add information from APO on top of that, returning to earlier level. Finally, this one, I have added more data. I wrote to the author of a paper that was comparing these two epochs from SDSS that was selected as a candidate for follow-up. And again, it changed completely. So those objects are showing a high level of variability, kind of beyond this 0.2 magnitude that you would expect. And I think that this method that is based on variability that can easily go through millions and tens of millions of objects, not necessarily with damped random walk, but you can plug in any favorite model that you want to fish out those candidates that should be spectroscopically followed up, is going to be very useful, because that's really the way to find those needles in the haystack and utilize as many different surveys as possible, rather than just restricting ourselves to a very, very short baseline. And we know from our simulations that very short baseline doesn't really give you much handle on the time scale, for instance, of damped random walk model or any other model, because you're not probing enough of the width of your light curve. So I think that's the last slide. Yeah, that's the last slide. So there's plenty of time for questions.
Time for questions. So,
I actually have two questions. So I think it's really nice talk. So the first one is like, is any of the objects you shown, are these multi-wavelength objects? Like, is there observation available at any other frequency?
Great question. Of those 40 candidates, the only one that had like X-ray infrared data was the one that already was followed up by Chelsea in her 2019 paper.
And on
the one where I
like,
showed.
I always wonder, so you like, have you looked into like how does the variability properties of these class of object compare to like the variable active galaxies? Those are bright and more variable, and the emission is more from the jet. So have you ever compared the variability properties of the two classes?
So do I understand your question correctly? Is it asking about comparing the properties of AGN variability to galaxies?
Yeah, the quasar variability actually.
So here we only have quasars in this sample. Those are spectroscopically confirmed quasars. So I do not have any galaxies in that sample, for instance.
Right. So I'm comparing like I'm just trying to understand like if there is some similarity or difference between the variability properties of like active galactic nuclei where the jet is pointed to our line of sight, more like blazars and these sources.
I see. Well, AGNs are lower redshift quasars. You could think of that way, but I do not have bona fide AGNs in here. Those are all quasars from Stripe 82 from Schmidt 2007 catalog. So it could be done. Yeah.
So did you check the distribution of Eddington rates before and after?
Where is it? Can we quickly go back, or do I need to click through them? it would be somewhere in the middle. Keep going. There you go. Yes?
No, but I mean for the change in looks, because like.
Oh, just to check Eddington ratio, but only for the
before
change.
and after the change of the lines. To
Yeah.
see if there is a transition at a given Eddington, because what we are finding from our studies is that at 1% Eddington, you see more or less this transition. Sometimes that's not reflected in the plot lines, but it's a transition in the state of degradation. So I don't know if you have seen this kind of.
So do I understand the question correctly? Do you imply to check objects that have here?
But I mean for the change in look candidates, not the.
That kind of to check those objects as candidates, or to check the Eddington ratio for the candidates?
If you see in your sample of change in look AGNs before the change in the classification or the change in the plot lines, there was a drastic change in the gradation rate.
So this would have to be measured, like based on this spectrum.
Yeah.
And I have not measured it yet, because you would need to. Pardon?
There is something you can do with the data you already have.
Yes, I have the data, but I'm looking for collaboration to fit it properly.
Oh, okay.
Yeah.
Now I understand your question.
Yes, that's why I was asking you about that.
Yeah. I think it's important to see, because I think probably you won't see all the time drastic changes in the plot lines, like the disappearance or the appearance, but you will see a drastic change in the creation state.
Yes.
And probably that will connect these very extreme variations that we're finding with the low amplitude variation. So maybe it's not just a matter of you are missing the lines. You don't have plot lines anymore. You have now plot lines. There's a change in the state of degradation. So it would be nice to see if you see that transition.
Yeah, so you'd need the 5100 junction luminosity and widths of H beta and all that. So yeah.
Okay, let's talk about that.
Yeah, I mean, my question is kind of related to the previous two questions. So you mentioned the training loop phase could be like a tail of the extreme variation, or like it could be some new astrophysics that is different from the general variability.
Yeah, I don't necessarily think it's
comments
different.
like if I try to design some observations, some experiments to tell the two scenarios.
Yes.
Which kind of evidence should I look for? So that is related to asking previous questions, like if the Eddington ratio is very different, then the accretion disk structure could change. I guess that's the point, right? Yeah. So do you have any comments like what kind of evidence should we look for?
So apart from extreme optical variability.
So whatever, it could be other wavelengths or like other time domains.
Yeah, so people have looked into, what could be causing this change, right? Could it be perhaps some sort of dust obscuration or something like that? And then you would be looking for some extra infrared excess. Or if it was some other source, the X-ray properties would change. So the additional information from other wavelengths could help distinguish one changing look scenario from another, because I'm not answering the question of what really causes that.
Yeah. I mean, I know it's maybe.
And it could even be a change in kind of like, a TDE, you have a short supply of fuel. It, has this characteristic T to the -5 Hz profile.
Okay.
We're not seeing that here because I'm talking about something that decreases or rather increases rapidly sometimes, but then stays at the same level for a prolonged period of time, much longer than the T to the -5 Hz power. So it's not those things do not look like TDEs.
Okay, thank you.
What about interactions of TDEs with the accretion disk?
Yes,
Then
so
it's not clear what is the shape, the Leica. So
yes, so it could be something else. Could be maybe a bigger source of accretion, such as an incoming, like in image of Kevin Shavinsky from 2010, this AGN flickering scenario, where your fuel comes and goes, then it increases the accretion for 10 to the 2, 10 to the 3, 10 to the 5 years. We know that there are AGNs that have turned off 10 to the 5 years ago, because you see those ionized clouds of gas that are still emitting, but the AGN is off. There is no X-ray from it. So we do know that these things happen on that time scale.
So did you remove the radio loud sources from your cell?
So this is the 9200 spectroscopically confirmed quasars from Stripe 82.
Yeah, but
I do not
can
recall.
contain radio loud quasars, right?
I do not recall if they are.
Just to comment, I try to match
Yeah.
with the VLAS, but yeah, I only have one case. It's not necessarily correlate with the radio variation.
But just going back to this issue of whether they're a distinct population.
Yeah.
I mean, can't you just look at all the variability measures of a group of these and compare it to the overall AGN population and look to see whether you just have every property just being the kind of extreme tail of an underlying continuous distribution, or whether you actually see some evidence for a bimodality or something.
Yeah, that's a good idea.
Yeah,
and,
I mean,
and in
that
fact,
might give you a strong hint.
an even cheaper way than doing the damped random walk fit was to take the difference in median magnitude.
Yeah,
You
right,
kind of
yeah.
get the same
Yeah,
outliers.
right,
You
right,
get
right.
that most of the objects are in the center, and it's a continuous distribution.
So you haven't, I mean, have you found any kind of variability measure you can think of where these things are, appear to be a separate population because of a bimodal distribution?
Yeah, I have not seen this bimodality.
Okay, so it's
plots I
always
made.
just extreme end of the tail.
Yeah, what I find in all my plots was a continuous distribution.
Okay.
This being the tail end.
Got it.
Yeah. Yeah.
I'm assuming that one of the important reference points that you have when looking for variability is the constancy of the forbidden lines, perhaps to a slightly lower redshift object. Do you ever see any evidence that you trust for an actual change in the forbidden lines, perhaps down in the wings where you expect the region to be closer and possibly of the same light crossing time, or are they always rock steady?
So are you asking about changes in different lines than broad lines?
Indeed, yes. I mean,
Yeah.
so you have broad H beta, but sitting right there are the two oxygen lines, which you, I would assume, always check to see that they are not in fact changing in general. So I'm asking, are there any cases where you do in fact see any changes? And I'm guessing that if you do, they're probably down in the wings, but it's an interesting astrophysical question.
Yeah, because this would be implying some changes in the narrow line region.
Yeah, which is normally thought of as a larger physical scale.
Yeah, yeah. Because it's also further out, so that's why the lines are narrower. And so perhaps those changes should be slower in the narrow line region than in the broad line region.
Absolutely. So do you actually see any changes?
So in the data yet, I have not done the spectral fitting yet. So I have to check if this indeed happens. But it's a very interesting, comment to check if there is the same rapidity of changes in the broad lines as compared to the narrow lines. Like the narrow lines shouldn't change as much as the broad lines do. I understand the point. If I understand the point correctly. Yes.
Okay, so we need to move on now. So let's increase again. And the next speaker is Vicky Sarajedi. So she's going to talk about variability properties for low luminosity AGN.
I'm sorry.
Yeah, you're gonna forward the slides.
You can do it.
Then this is, I just ship this back. This one?
Yeah. Oh, I'm sorry. I should.
This one.
Yeah, the screen was not shared yet.
Great. Great. Well, it's a pleasure to be here today to speak with you. Today, I'd like to talk to you about some variability properties for a low luminosity AGN sample that we've been studying. My collaborators on this project are Kritipas Chenchai-Warwit at the Thai National Observatory and John Della Costa at NOR Lab. We are interested in a lot of the same questions that we've just been talking about at the end of the previous talk. So whoever arranged these talks did a good job grouping them together. So in particular, we know that there are these relationships, right, between AGN characteristics of the AGN itself and the light curve properties. One of the ones that we've talked about already is this anti-correlation between luminosity and variability. And this is the plot, I think, from Simidal 2016. So various versions of this have been noted over a couple of decades, probably at this point. And one of the big questions is what's really driving this relationship? Is it, is it the luminosity, or is it the black hole mass, or is it the accretion rate? Most people find that the accretion rate seems to be the larger contributor to this trend. Black hole mass, different studies show different things. Like sometimes there's a positive correlation, sometimes a negative correlation. And so that kind of seems to be a secondary effect towards this relationship. So a big question that we were discussing at the end of the previous talk is, what's going on as we go to these lower luminosities? Is there, just a continuing trend of these relationships just becoming more extreme, right? As we go to lower luminosities, lower accretion rates, lower black hole masses, or do we see a shift, a change possibly into a different kind of accretion mode? We know that at some point, probably the standard accretion disk doesn't really well describe the systems. At some level, we could get into sort of ADAFs and other kinds of accretion mechanisms. So the question is, do we see that eventually? Can we probe low enough luminosity? So I'm going to describe a sample that we have selected from Sloan that get to pretty low luminosities, and we can determine the accretion rates and the black hole masses. And from that sample, we can do some ensemble variability statistics. But then with ZTF light curves for most of those sources, we can look at more specific examples of the light curve characteristics. And possibly this could be a nice training set for trying to uncover this type of object with LSST. Okay, so the sample that we selected is from the last, I guess, Sloan data release. And to look for low luminosity AGN, we pretty much did something pretty simple, which is just to find things that had extended morphologies, but also had a broad emission line. So in this way, we were hoping to find things that are, relatively low luminosity. With these data in Sloan, it's coming. There you go. We can do some ensemble variability statistics. So that means that, we don't have a full light curve, but we do have 2 data points for every object, right? We have the photometric measurement taken when they took the image of the sky, and we have a spectrophotometry measurement from the spectrum. And so we can compare just those 2 points for a whole bunch of sources, right? And as if we had one light curve, but we don't. We just have lots of different points on several different objects. And so this is how we would do an ensemble variability statistic. So to do that, we have to also define a normal galaxy sample that will give us our noise characteristics as a function of signal to noise. And that's what we're showing here in the 3 bands that we looked at. This is just showing the difference in magnitude between our 2 points for every source. And you can see the normal galaxies are the dashed line. The width of those are going to be less than for the broad line objects. In the G band, you see it to a greater extent than in the I band. Presumably the host galaxy is contributing more as we go into these redder bands. Okay, so host galaxy, right? It's a problem. We have to figure out how much of that is contributing in each source. So it's very important to do the spectral decomposition. And we did that using principal component analysis by reconstructing the spectrum using a linear combination of eigenspectra and some templates to represent different AGN and host galaxies. So by finding the right level for each of those, we could estimate how much of the spectrum is from the host galaxy and how much is coming from the AGN. And we need to know the luminosity of the AGN, so we have to determine that. Also, we wanted to study the spectrum, the AGN spectrum, very carefully to get the broadline measurements. So we have to subtract the host galaxy for that. So here's a few examples. Oh, I should have said there are about 35,000 objects that met our initial criteria from the Sloan database that were extended and had broad lines. And we went to fit these with the PCA eigenspectra, and we were able to have pretty good fits for about 2/3 of those. So we're kind of slowly diminishing our numbers here, but this is an example of one where you have a host galaxy dominated spectrum, right? There's very little AGN in that. I think this is like 80% galaxy. And here's one where the AGN dominates, right? So you can obviously see the broad line features much better. We end up kind of throwing out a lot of these just because, you know, it's very difficult to get a good handle on the AGN luminosity in those cases. But all in all, it worked very well for, you know, the majority of our sources. Okay. So this is a plot showing this host galaxy fraction where this is all galaxy, right? And this is like all AGN down here. And then this is as a function of apparent magnitude. This is the absolute magnitude of the AGN component, right? So if we account for the host galaxy. And this just shows our redshift range. Oh yeah, so as I mentioned, you know, H alpha or H beta were present. So we had to have H beta. So we have a limit of 0.8 there. And then this is our spectral signal to noise. So you may be wondering about these different colors here. They represent kind of a shift in the data release, the Sloan data release that happened in 2009, where there was a change in the detector and also the survey parameters. So because of this change, we had to treat these two kind of data sets separately because the noise characteristics were quite different. As you can see, the stuff later, that was taken later, that's the orange data here, are at higher redshifts, lower spectral signal to noise, and the noise characteristics in general as a function of signal to noise are also a bit worse. So we treated those two sets separately. But in order to be confident that we could recover the AGN component and the host, you know, separate those two, we did a number of simulations to determine how certain we could fit the host galaxy contribution. So we basically just, you know, made simulated spectra where we had various fractions of host galaxy to AGN as a function of signal to noise, and then went back in and fit those multiple times to see how well we could determine the host fraction. And we cut the sample to include only sources where we had a 95% certainty or accuracy of being able to recover the host galaxy fraction that we put into the simulated spectra. So when we did that, of course, we end up losing a lot. Yeah, and I'm sorry, this is kind of flipped now. I don't know why, 1 minus psi. So now you have, this is where you have all the host, and this is where it's AGN. So obviously where the host dominates, you know, it's a lot harder to recover and at low signal to noise. So there's kind of a contouring here that says 5, that's at the 95% accuracy. Everything up in this part, we could recover fairly well. So if we apply that cut, then you can see it kind of cuts out a lot of the things above 80% host galaxy and things that are less than a spectral signal to noise of about 7 or 8. And that does give us a few kind of artificial relations here, but we can, you know, we can see those later and account for them. So we'll just be aware that that's part of our selection. Okay. So once we subtract the host galaxy, we can look at the AGN spectrum and do some precise measurements of the H beta line. So we used H beta to determine the black hole masses for each of these sources in our sample. And we're down to about 9,500 sources now. So we're at, you know, close to 10,000 objects in this sample. And the we got the black hole masses using H beta and the Park et al. Scaling laws. And these plots are just showing, you know, various combinations of the different properties of this low luminosity sample. Let's see, probably one of the best ones to look at is right here, because this is the black hole mass here, and this is the accretion rate. So here we have the Eddington accretion ratio. There are some limits here placed on our survey based on our requirements for the full width half max of H beta. But what I want to draw your attention to is that this sample really probes very low luminosities. And in fact, if I show you here these X's, that marks the median values for the Stripe 82 quasars that are generally used for these studies. So you can see that we're about, you know, 20 times or more less luminous is the median for our sample, and the median accretion rate is around 4% Eddington. Obviously, the redshift range of the Sloan quasars is much higher. That's why this arrow is here. But I think, we were able to achieve our goal of pushing down into, kind of a different parameter region than we normally are studying the variability properties for with this sample. Okay, so like I said, the first thing we can do right off the bat is measure some ensemble statistics. And generally what you've seen before is people will make a structure function. Usually a structure function, kind of it goes up and then it kind of levels off. But because we're looking at an ensemble here, we can't really do that, right? We're just looking at the slope because it kind of smears out the characteristic time scale. Isn't really something you can measure, but we can look at the slope, the rise basically of the variability as a function of time. We define the structure function with this equation. There are kind of various ways people do it, but this is kind of the simplest way, where you're really just subtracting off, your photometric noise from your time differences. And we're comparing our results here, which are shown with the dashed lines, which are fits to the points here in the G, R, and I, to a sample, a kind of a similar ensemble sample that was published a few years ago by Yi et al., where they looked at quasars from decals and from Sloan, 120,000 of them. And you can see that the slopes are pretty similar. The difference being, of course, that our sample is going to be at a higher overall amplitude because of the lower luminosity. So this is what we've seen before, this kind of increase in amplitude of variability as a function of decreasing luminosity. I know they look a little different, but within the errors, the slopes are pretty much the same. And I should point out that we kind of extrapolated their work down to lower time intervals, where they really only kind of fit the data down to about a year. So we would find that the sample at least is largely consistent in terms of the slope of the ensemble statistics with quasars. Okay. So here we're just binning now in terms of absolute magnitude. So this is showing more clearly the anti-correlation of luminosity and variability amplitude. So I don't really know what's going on here. This was not as smooth as I thought it would look. So what's happening here? Usually you find that the G-band should be a little bit higher than the rest, but I don't know, you may have some weird data points in these particular bins here. But in general, the trend is consistent with that. But what's interesting is that even down, to these pretty faint absolute magnitudes, we're still seeing this decrease, or I'm sorry, this increase in amplitude, right, as a function of decreasing luminosity. And so we're going probably, 3 or 4 magnitudes fainter than previous studies to kind of probe this relationship. Okay, so the Yi et al., or sorry, Lee, I'm sorry, I'm using the wrong paper. Lee et al. 2018 also looked at accretion rate for the quasars and the black hole masses, and also probing this question of variability amplitude as a function of these different properties for their black holes. And this is a plot of their black hole masses and accretion rates. And the color coding here is just showing the variability amplitude, right? So that you can see as you go down in accretion rate, the amplitude increases. And they also find a slight correlation, a positive correlation with black hole mass. And they also did some multidimensional fitting of a whole bunch of parameters, all these parameters basically, as a function of amplitude, and determined that the accretion rate relationship was the dominant one, the most significant one in their sample. So we made a similar figure for our data. And again, you'll notice that we're going down here down to like what 7.7 is the middle of ours. So we're going down, at least 50 times smaller in black hole mass. And like I said before, much further down in accretion rate. So we kind of occupy the space down here. And again, seeing a similar trend. It's not really changing, right? As we go down in accretion rate, you see us going up in amplitude. And we're not seeing much relationship at all in terms of black hole mass. So we're not noticing that the amplitude of variability is being impacted by the black hole mass when we get down to these very low masses in our sample. Okay, so with this data set now, we can expand upon this and cross-correlate it with the ZTF survey to look at more more, a larger range of variability properties with full light curves for many of the sources. And these two surveys are really well matched in terms of apparent magnitude. So that means that pretty much all of our properties are very well matched. So this orange histogram here is just showing the ZTF, the ones that have ZTF light curves in our sample. So far, we just looked at the G-band light curves, but we plan to do this with R and I as well. And you can see that they're well matched in terms of bolometric luminosity to our overall sample from Sloan, black hole masses, and accretion rate. So this is just showing the ones that we could get the ZTF light curves for currently. And we limited this to sources that had at least 30 good epochs in the latest data release. So here's an example of one of our sources from our sample. This one has a host galaxy fraction of about 37% and a pretty low accretion rate at about 1% Eddington. And here's just to show you what the ZTF light curve looks like for this one. And you can see that it's a lot, you've seen light curves before. There's a lot of variability here. The amplitude is pretty high for the variability. And here's one where you see that the host galaxy fraction is more than 70%. So this is kind of getting near the limit of what we might have not included in the sample. So we're seeing something where the host galaxy is going to have a very large impact on the data, and this is what the ZTF light curve is here. You can still see some variability, but clearly there's an impact here. So I think this is going to be really important data set to use because we know the host galaxy fraction contribution. We can use this to help us understand how that's going to impact our the kind of light curves that we would expect for this type of galaxy in LSST. So to do the light curve analysis, we're using the software EasyTau, which is a nice set of algorithms that will allow us to fit the DRW models as well as the DHO models to these light curves. And as was mentioned in the previous talk, the DRW is nice because it's defined by these two parameters, tau, the damping timescale or the decorrelation timescale, and the amplitude of variability, so just two parameters. DHO allows you, as a damped harmonic oscillator model, allows you to fit a sort of fuller suite, I guess you would say, of light curve characteristics, but does require more fitted parameters. So therefore, it's a little bit harder to do. You not only have a damping timescale, you have a damping ratio, a perturbation timescale, you can fit the white noise amplitude, as well as an oscillation frequency. So in DHO, you can look for quasi-periodic or periodic light curves as well. We really just started working on this, so that's why I'm calling it the initial results. And so we're trying to do this just for the ones that are the most variable. So we kind of set a threshold here for things. This is the RMS of the ZTF light curves and the G-band magnitude for our sample. So right now we're just looking at the ones that are kind of above this sort of arbitrary threshold for variability amplitude, and also ones that were deemed to have good fits based on some characteristics from the Yu et al. Paper, where they've done a fairly extensive analysis for the Stripe 82 quasars with DHO models. Okay. So first I'll just show you the results for the DRW parameter fits. And we're comparing these to Kozlowski's 2017 work here for the about 9,000 Sloan quasars from Stripe 82 again. And he plots these with redshift versus absolute magnitude, and the colors represent the decorrelation or damping timescale in this case, and here is the amplitude, right? So what you notice in this plot is that as you go to lower luminosities, right, you're seeing that the decorrelation timescale is getting shorter, right? So that would mean a steeper sort of structure function, right, or a steeper slope in that relationship. And here are our data here extending, down into this part of the diagram, much lower redshifts, of course, but also much lower luminosities. And we're seeing pretty much the same trend, right? Whereas we go down to lower luminosities, we're getting steeper and steeper slopes. About the same thing in amplitude as well, right? So as we go to the lower luminosities, the amplitudes are increasing somewhat. Although, I mean, in this case, you can see that it's a bit more mixed, right? So we're starting to see that it's not quite as clear, I would say, as with the quasars in this case. So we're still kind of analyzing these data to better understand how to interpret this. And then finally, like I said, we've just started to do the damped harmonic oscillator fits to these light curves as well. This is a plot from the Yu et al. 2022 paper, which nicely shows how the Sloan quasars fall into different categories when we plot the 4 different parameters versus each other. You can see that, and this one in particular is helpful because it shows what they call the overdamped and the underdamped light curves. And over here in the underdamped is where we see the quasi-periodic oscillators and other oscillatory light curves. And this is the more, stochastic kind of traditional, I guess you might say, light curve for quasars. And when we look at the initial results from our survey, they pretty much all fall over here in the overdamped region, right? We hardly see anything in the oscillatory region, and that might be expected since this is such a low luminosity sample. The parameter ranges are similar, although we do find that we're extending to larger values for the damping ratio and higher frequencies, natural frequencies. In this plot as well, our parameter range is a bit broader. So again, we're still kind of doing some tests because there are probably some corrections we need to make to this based on our noise characteristics, which will be impacted by the fact that there are host galaxy light contributing to these light curves. Yeah, and this is just to show you in our sample, we have a lot of very low accretion rate sources. In fact, there's more than 250 that are accreting at less than 1% Eddington. And we're really interested in studying this sample because those in particular might be this place where we could be switching into a different accretion mode. So we might start to see some changes in the variability properties there. And here's just where those ones that are less than 1% Eddington are lying in these particular regions. So at this point, we're just kind of identifying those interesting objects and hoping to do more analysis on those light curves. Right, so that's it. So just our conclusions here. In the future, we hope to continue to analyze the light curves more closely, especially for these low accretion rate sources, so that we can better characterize what kinds of variability properties we can expect as we push to these lower luminosities and basically the extremes of the population, which are sure to be a pretty big part of what LSST is going to be finding in the future. So, thank you.
Have you done any work in the Rubin footprint? I mean, unfortunately, of course, Sloan, where I think you've focused, is not overlapping so well with Rubin. So to prepare, you'd want to develop a similar sample down in the south. Have you made any progress there? Are you thinking about doing such a thing?
Right now, I'm not sure if there's I'm not sure if there's a similar type of set of data that we could use. I mean, presumably, the characteristics should be similar. I mean, it should work anywhere. So if we can define like what we expect to see, then if we see similar light curves like that, we might be able to map out like where they are in that parameter space.
Right. Yeah, so like Sloan 5 now is starting to get a good number of Sloan-like spectra in the south. And of course, DESI.
Yes, yeah, that's right. I mean, actually, yeah, I mean, it wouldn't be hard to do, right? I mean, it's just a very similar, it's a very simple way to select. And once you can, if you have the spectrum, then you could get all these other properties and you would know precisely where the low luminosity sources were.
Yeah, could be a good thing to do before Rubin starts up.
Yeah, that's a good idea. What was this?
Could you elaborate a little bit on your statement that you don't see periodic systems, but it's not unexpected because they're low luminosity? What's coming behind that?
I don't know. I mean, I think that was just my initial reaction when I saw that plot was like, okay, well, maybe that makes sense because we're not looking at, these are probably things, like I said before, because they're low luminosity, maybe they're low accretion rate, they're kind of like under the radar where you're not seeing like maybe big tidal disruption events or things like that might also indicate more of a oscillatory nature, but I don't really know that. I mean, I'm just kind of guessing.
Okay.
I did not understand one of your slides where you showed the histogram of your sources overlapping with SAT?
But, on the histogram, you mean?
Yeah.
Back here.
That's this one. Next one.
Oh, sorry. This one?
No, there is a histogram.
I think you passed it already.
Sorry.
Yeah. So the blue ones are your real sample, and the orange are the counterparts which you found in CTF.
Yeah, these are just the ones that match sources in ZTF, just to show that the ZTF light curves are still probing this full range of luminosities from our original sample, as well as accretion rates and black hole masses.
Okay, but this is the number of the sources, right? So how can it be different for the different plots? Maybe.
Oh, I think these are just the way the binning was done. Yeah, so.
Okay.
They're not the same bin sizes, so I'm sorry. Yeah.
So you're using data-release linkers, but these sources are very host dominated, right? So there's going to be a lot of noise just because they're extended in the images. So are you correcting that somehow?
You mean for when we do the ensemble variability? Yeah, so so we do have to correct that. Yeah, so there's some steps in there that I kind of passed over quickly because the fibers are a certain size, right, for the spectrophotometry, and they do this PSF fitting for the actual photometry, and there's an offset in there. So we actually model that and make a correction so that it's all kind of zeroed out. But it is a function of the signal to noise. So basically a function of how bright the source is. But yeah, there's going to be some noise added to that simply because, galaxies have different shapes and, but based on the seeing that, I think it's like a 3 arc second or so fiber.
Yeah, but that's to measure the contribution from the host. But I mean, in your CTF likers, the sources will look extended. So you might have some flux from the host entering the PSF, and the contribution from the host would be different every night. So that would produce fake variations in the liker. So
yeah,
I
don't know, but I think that'd be something that, because we know the host fractions, at least from the Sloan spectra, we could use that as a starting point to kind of estimate like how that does impact the light curves, so that we could at least be able to kind of predict what the result would be. I don't know if we can correct for it. I'm not really sure how to.
So probably the solution would be just to go and do your own photometry, which is super expensive.
Right, exactly. So the best, I think the best we could do is, be able to quantify it, right? Maybe as a function of the size of whatever is the photometric measure.
A suggestion. So now it's not available yet, I think, but they are going to release a better version of the force photometry service. Is it available?
You mean Supercall?
No,
I think
it's a service where you, instead of getting 100 likers per day, you can get 1500. It's available? Yeah. Oh, nice. So then you can download in, I don't know, a week the whole sample, and that's force photometry over the different images.
For the ZTF curves. Yeah, okay.
Remove the host.
Oh, well, that would be very helpful then.
And this is something that I wanted to point out also, because you saw a couple of examples of light curves where you see a lot of variation, but I guess from all of your samples you will have some light curves where you don't see that amount of variation. And that will be a problem also for the same reason.
Yeah.
So how do you deal with that kind of variation? I mean, how are you? Because for example, the errors might be a problem in those cases. So are you applying like something to estimate the variability?
Well, for the ZTF stuff, we really just started looking at these light curves. For the ensemble, we attempted to kind of correct for the host galaxy contribution, like how much we expected it to decrease the flux change, and we kind of increased it by the amount that seemed that was consistent with the contribution of the host. I don't know how we can do that for this, but I think probably going towards more of a variation. Now, you said that this is now released for ZTF through.
Yeah, it is. With Paula, we can give you some advices on.
Yeah. Okay. Yeah. I'll talk to you later and get some.
Okay. Okay. So we have to move on. So thank you again. the last talk of the session would be by Rani. He's going to talk about unveiling the dynamic nature of active galactic nuclei, statistical tool for LSST AGN variability.
My talk is pretty short.
Okay.
Yeah, sure.
Thank you. And my name is Bindu Rani. I work at NASA Goddard Space Flight Center. And I will continue talking about AGN variability, but I'm not going to bore you with the faint AGN. I'm going to talk about the really bright sources, and I will also talk about some of the results from the recent X-ray that are taken from recent X-ray missions. But again, the study, the tools and the kind of study can also be used and applied to the Rubin datasets if they promise me to, provide a high cadence light curve for a longer period of time. Otherwise, we need to find other ways to extract the scientific knowledge from the data. I don't think I need to talk to you about AGN because the previous talks were on active galactic nuclei, but the one thing I want to point out is that I'm talking about the AGN where they launch relativistic jet, and one of the jet is actually pointed close to our line of sight. So as a result, what we see is that these sources are super bright, extremely variable, and a very interesting object to study. And they are even more interesting because of the fact that given the, thanks to the recent X-ray missions, we can probe the X-ray variability on time scales of the order of few minutes, which is, we are probing the event horizon time scale using the X-ray observations. Moving on, so there are two topics I'm going to discuss today. The first is AGN variability, and I'll try my best to convince you that AGN variability study is really important, and we could extract a lot of, it's a potential discovery space as being recommended by the ASTRO 2020 decadal survey. So we need to invest a lot of time in developing our statistical tool, even if our data is not evenly sampled. The second half of my talk is dedicated to a statistical tool. I will talk you a little bit about the tools I used and why I'm particularly interested in that particular kind of tool. And then I'll also discuss that that tool, even it is meant to be used for evenly sampled data, how we can modify the tool to use for unevenly sampled data. So that's a typical AGN light curve. AGN spectral energy distribution looks like. You can see that here the contribution from different different parts of the AGN, and as I said, I will be talking about mostly about AGN that has jets, but some of these sources also have a significant contribution from the accretion disk as well. So this is a range, more or less, Rubin will be probing, and we might be getting some contribution from the jet and some contribution from disk as well in some of the disk bright sources. So first thing first, why do we care about variability? Well, first of all, these sources vary and they are interesting to study. And if we do that, we can extract the physical information about how these systems work. We can extract the variability parameters. So we can try to connect the variability parameters at different energy wavelengths if we use the cross-correlation analysis studies. And we can understand how the different components of an AGN works and how they are how the system overall works. And it's also, I don't need to repeat that again, but it's also a very important tool to identify AGN. As you have seen that the variability properties of AGN is very different from the variations we see from non-active galaxies or from other optical bright sources. This is the This is an AGN light curve. This is how the light curve of a typical jet-dominated AGN looks like. So it's variable and it's bright across the whole electromagnetic spectrum, starting from gamma rays up to radio, and even we see variations in the radio jet as well. There are also component motions you can study and try to connect the dots and put together a picture of the whole AGN system. And if you do that, you can clearly identify the different emitting components at different radio wavelengths, also at X-rays, gamma rays, and you can pinpoint where the different emitting components are located in the jet. So broadband variability study is a very important and it's a very useful tool to probe the different emission component, and also to understand how the central engine of an AGN works and how it feeds and regulates the jet. So what Rubin will offer us will be the time domain variability in optical band and multicolor variability. But the unique feature about Rubin is that it will take us a few thousand of AGN to millions of AGN. And I was hoping we could get some uniform cadence for some period of time, and I will try my best to convince but I feel like it's a bit late to do that. And I think Rubin will also provide, the sensitivity level of Rubin will be also much better compared to the previous observatories. So we can use that data to probe the to probe the emission regions, especially at optical bands. And again, as I said, some AGNs where the optical emission from some AGN is actually dominated from the jet, and in some cases it's coming from the disk. So there could be cases where one part of the optical, for example, if I show you, if I go back, no, not possible. Can you go back? Yeah, just two slides. Okay. If I show you this particular light curve, it's an interesting light curve, but I don't have all the opticals. So for example, for this source, the UV and optical bands, the optical band up to UBV and bands are dominated by emission from the jet. And when you look at the I and R bands, you see a clear contribution from the accretion disk. And if even using like simply the optical variability studies, you can study the disk jet connection in the source. There are not that many AGN where you see optical, you see contribution from both the disk and jet, but there are few sources, and this makes our disk jet connection study so much easier. One given wavelength range, and you can do a lot of science together. So moving on, so for us to extract the physical parameter to understand these systems, we need statistical tools, and we need statistical tools so that we can extract the physical parameter. And we also need those tools will increase the scientific return of Rubin and other observatories as well, and will maximize the scientific return of the AGN variability studies. So in my talk, I will particularly talk about a tool which is called power spectral density analysis method. And it's basically, if you have an evenly sampled data, it's basically the Fourier transform of your light curve. So if I talk about a given, let's say, let's talk about the AGN intensity variability as a function of I. If you look at the variability light curves, this is typically how it looks like. And if I look the same light curve in the Fourier domain, it's basically what we have is the square modulus of the discrete Fourier transform. And this is how it looks like. We have power as a function of temporal frequency. It's not as simple as I have drawn it here, because this is just a cartoon. It could also have slopes. It could also have breaks. The normalization factor is important as well. And we could also hit the Poisson noise depending upon the brightness level of the source here. So again, it could also have multiple breaks as well. Each slope has bring a unique information about the variability characteristic. The breaks are important as well, and the breaks are found to be significantly correlated with the physical properties of the system, like attrition rate, like black hole mass, and that tells a lot more about the system. in journal. So this is an example using X-ray light curves. What they have done is they have extracted the characteristic time scale which correspond to the break time scale in the system, and they plotted it as a function of black hole mass. And as you can see that the smaller black hole masses, they have smaller break time scales, and the larger black hole masses have larger time scales. So which means that the characteristic variability time scale in an AGN scale as a function of black hole mass. And it also depends on the other physical parameters like luminosity, and it could also be related to the accretion rate of the system. And there are other studies performed as well, but I will not go into the details of those parameters. What I want to talk to you about is something new and exciting I started working on recently. So this is actually the data that came from the NICER mission. NICER is an X-ray mission launched in 2017, and the best feature of NICER mission is that it gives us temporal variation sampled at that at time scales that was not possible before. The shortest time scale you can sample is at the rate of around 300 nanoseconds, which is not possible because AGNs are not that bright. But for bright AGN, we can sample the light curves at a rate of few seconds or so. So these are the NICER observations for an AGN NGC 4051. It's a Seyfert galaxy. The X-rays, the source has a black hole of mass of 10 to the power 6 solar mass, and the variability light curves are sampled between 2017 and 2022. So most of the X-ray emission in this source, we know that it's a Seyfert galaxies, and from the spectral studies, we know that X-rays are coming from the inner part of the disk. So in the light curves, this is the 2-second sampled light curve here, and you can zoom into the faster events, and you can even zoom finer into the big events, the big flares. So here we have the 2-second sampled light curve of the source between energy 0.3 to 3 keV. So as you can see here, variability studies on this time scale was not possible before, and I was hoping that Rubin can provide us something similar. And I'm still hoping for that. So time variability study, as you can see here, it's a potential discovery space. And we don't know what we discover when we study the AGN variability on those time scales. So before I show you the PSD analysis curve for the light curve, I want to talk a little bit about the NICER observations. So NICER observations, the maximum NICER can observe a given source is for 2 kiloseconds, like 2000 seconds. So we have these evenly sampled 2000 seconds long light curves, which are unevenly sampled on long-term basis. So something like this. So each data chunk is around 2000 seconds long, and then it's evenly sampled over here, but then there are gaps in between. So if you look at the PSD of a given data chunk, which is about 2000 seconds long, this is something how it looks like. And now the question is that how do you combine? We need to bin the we need to bin the PSD, the power spectrum density analysis data, and we need to extract the physical information from there. So one way is to bin 50 data points in that frequency range, or other way is that you can calculate the PSDs for 50 different time segments, and then you can bin them in that direction. And if you do that in that way, you are not losing your frequency information. You have as many points as you could have for your raw PSD. And as I have shaded this area, this is a potential new discovery area. PSD studies on those frequencies were not possible before, and those studies have only been possible from NICER observation because it allowed us to probe the time scales which were not possible before. So there could be, this is one source where we do not see hint of a secondary break, but there could be sources where we have multiple breaks. When you compare the X-ray variability properties of AGN with X-ray binaries, in case of X-ray binaries, when they go from soft state to hard state, their PSD shapes are completely different. Here, in case of AGN, we don't have that opportunity because of the fact that we don't have observation sampled on time scale that can probe the secondary break in most of the systems. So NICER opened a new opportunity window for us to discover and to study the frequency domain. Okay, so that was all about studying the PSDs of X-ray light curves from AGN using NICER, and we can use the tools we have for NICER analysis for Rubin as well if the data is evenly sampled. Otherwise, we need to think about other ways to incorporate into our unevenly sampled data. The next topic I have in my talk is the QPO studies. The same method can also be used to hunt for QPOs in our light curves. Again, this is the simplest version of a PSD and a QPO sitting on top of that PSD. So if there is a repeated frequency, the power corresponding to that repeated frequency or QPO should be higher than rest of the should be higher. It should pop up higher in the PSD. So one important factor here to note is that we need to constrain this red noise or the PSD slope well in order to detect the significance of this QPO. And most of the methods that are available in literature, they are not successful, fully successful in in detailing the underlying red noise powerless slope when they are looking for QPO signals. So for example, what do you think about this light curve? This is a gamma ray light curve for a source 0716 from the Fermi Light Curve Observatory. And what do you think about this light curve? Do you think it's periodic? Does it look like periodic to you? Any guess?
Maybe.
Anyone else? So the fact is that there are papers in the literature. If you look at QPOs in gamma rays, then you can even on Google or archive you can find hundreds, thousands of papers where people are using gamma ray light curves and they use their favorite tools and they claim like different QPO timescales in different sources. And there are like 2 or 3 papers on this source also using the same light curve where they claim QPO detection in the source of the order of around one paper says 13 days, one paper says 30 days, and one paper says, I don't remember the third time scale. Anyway, let's take a look at the PSD analysis of this source. So this is the raw PSD, just Fourier transform of your data. Then I bring it into frequency domain. I have to do that. And that is the binned PSD in blue. And that black line corresponds to the best fit power law. And it has a slope of roughly -1, which is consistent with the red noise process. And as you can see here, this is the 3 sigma line. If there is a QPO, the power should pop up over here. And since there is no signature of a QPO in this source, you can clearly see that there is, the light curve is not periodic. And when we are looking for periodic signals in our data, one has to be very, very careful because, determining the underlying red noise slope is very important to calculate the significance of a QPO signal. Okay, so I think that is my last slide, and I would be happy to take questions after that. So as I said, Rubin will observe sources more than few tens of millions every night, and those sources are, most of those sources are going to be variable, and the variability observations will be done in multicolor. So we need to think about preparing our statistical tools so that we can extract the scientific information from our data. And since the data set are huge, we need to automatize our tools. And as I said, PSD is a promising tool for extracting the variability time scale and relating the variability time scale to the physical parameters of the system, and also for QPO detections. And one thing I didn't cover in my talk because I thought that it's going to be only for 20 minutes is the fact that when Rubin is observing the optical sky, there are observatories which will be looking at the optical sky in other wavelengths. So one thing which is also important for us to consider to find the synergies and how to maximize the scientific return of Rubin in coordination with the other observations. So like X-rays or, well, Fermi is scanning the gamma ray sky. So anyway, those observations are for free, but especially for with X-rays and X-ray polarization and maybe like the future missions like Roman. So we need to prepare for those as well. So that is my last slide, and I would be happy to take questions now.
Just one thing I'm a bit puzzled by. So, regarding a source like NGC 4051, I've been studying NGC 4051 in the X-rays for 25 years. Okay, and certainly it varies in very interesting ways on rapid timescales. That's been well known for 30 years.
Yeah.
The question I have is, you seem to be taking that fact and then using it to argue, well, that means Rubin has to monitor that fact. But 4051 doesn't vary like that in the optical.
I totally
It just
agree.
doesn't.
I totally agree with you. The reason why I showed you the nice result is because of the fact that, every instrument or every facility have its own capability. And nicer capability is to provide fastest possible observations. And Rubin has its own capabilities as well. So we need to think of the ways how to harness the science that's hidden there in the data.
Yeah. Certainly agree
So
with that.
I give that example of NGC 4051 because of the fact that we were so stunned by the results. I haven't showed the final.
By what results? The fact that it varies on timescales?
No.
tenth
The
of a
fact
hertz?
that there is power on higher frequencies as well, and there is a secondary break, which I didn't show because I still
We've
need
known
to
this for
test it.
20 years. I mean, we knew this from XMM.
Yeah, we
And
knew that from
gives us-
XMM, but
yeah.
XMM only goes up to a frequency of 0.01 or so. XMM doesn't go to a frequency of 0.2. So there are like
XMM, well, I mean, you hit photon limit. Anyway, we can talk about this offline if you want, but you get plenty of photons with XMM.
No.
Up to very
I
short
totally
time
agree
scale.
with. So
You may be extending it by a factor of
I'll
2
show
or
you my
something,
results
but-
later. I'll show you my result. I will convince you before I leave the conference. So, but the point was that XMM goes to a frequency of when you translate your sampling rate to in frequency domain. XMM goes up to a frequency of 0.01, and then it starts to hit the Poisson noise. With NICER, the source is twice as bright. Plus, we can sample at like frequencies of the time scale of the order of around 2 seconds. So that takes up to frequencies up to 0.2.
You can, the sampling is the same for XMM. You may have a little bit improved photon statistics, but
Yeah.
of course you also have much worse background.
Sorry.
Oh, I was wondering about S50716 plus 716, the one that you said 2 or 3 papers have detected 13-day QPO. Did they use the same data and method? Based on what method did they find?
So they use. So one of the paper I remember is that they use one paper used Bloom-Skarger periodogram, and I think they also used wavelet. I don't remember what the second paper used.
So but based on the same data, or
It's same data.
how is it that you're not seeing that?
It's not there. If it is there, don't you think every method should be seeing that?
It should be, and that's why I'm asking if
Yeah.
it's,
So
if it's not,
my
for instance,
impression
the
is
sampling
that,
issue.
taking care. It's very important to constrain your red noise first when you are hunting for QPOs, and I believe that's not done. That's not the case when you are using other methods.
More questions?
Have you considered using Hypercam on GTC?
No, but I think people are using that. Yes. No, I haven't. I haven't used it.
Because that has much faster readout than LSST. Like you can get 1000 hertz.
And I think at some
5
point we
octopus.
need to use them because the data is not going to be evenly sampled. I'm sorry. What was it?
I have another one. Just,
Oh, so on.
so regarding AGNs that could vary on timescales of order 15 seconds or a minute or something like that. As you mentioned, I think the blazars would be the most likely ones that would be doing that. my understanding is that the blazars are rare enough on the sky that using a 10 square degree field instrument to repeatedly count on a single blazar is not really the right way to go about it. You'd want to use a much narrower field instrument.
That's so true. That's so true.
Okay.
But it's also another factor which I don't think I mentioned in my talk. It's also important to look at the variability properties of the sources, which which are not detectable. Even if the data is not evenly sampled, but like looking at other jetted AGN, other radio loud AGN, which are faint, and compare the population study of radio loud jetted AGN with the low luminosity AGN. So one thing is I find quite interesting in the previous talk was that they see an anti-correlation between AGN, the source brightness, and the variability amplitude. On the other hand, when we look at the sources like the bright AGN, which has set, the variability increases with the amplitude of the brightness of the source. So so that's one thing. It's important to compare. So I think those are the questions we really need to look at. The attrition rate, I'm not sure, because it also, I don't have enough knowledge to speak about that, but I think the attrition rate and variability relationship could be different in different class of object as well. But,
sure.
Nobody has looked at that.
Well, no, that part I disagree with. There have been extensive searches for intranight variability among radio quiet AGNs and radio loud AGNs of various types. And they generally find it among the blazars sometimes. Some extreme blazars show it in general, the other ones at least haven't so far.
But when I was preparing, to be very honest, when I was preparing this talk, I always had in my mind that I'm going to get the beautiful light curves, evenly sampled light curves, at least for some sort.
No, but you have to have some science motivation for it. You can't just say, I'd like it. So
no, I understand.
There's no evidence you're going to see much of anything among, I mean, you might get something among the blazars, but they're, again, very rare on the sky and are best hit with narrow field.
So which is why one of the, I showed that nicer light curve just for the motivation. Anyway.
I mean, if there are some observational evidence out there, we should take it into account, but I'm not aware of any. Yeah. Okay.
No questions? So you were planning to use your technique that requires evenly sampled light curves with LSST, but that's never gonna be the case.
I learned my lesson. No, that's not gonna happen. But yeah, as Niel said that I think the right path here should be look at select some of the really bright and variable optical AGN. Use Caplar or TESS, one of those, same band as Rubin has. Look at the variability properties and see what investigate and see what we see. And if there is something interesting, then we can. It's easy for me at least to convince you and you to convince us.
Well, I know that part's not.
If I can continue with my question. But there are other techniques that allow you to do this with uneven sample data. So are you planning to implement those?
Well, I have used, I started my career with optical astronomy, and most of the data was not evenly sampled when I started. And I have used all of them. And I've noticed that, this evenness and other stuff, that evenness in the data and data gaps, when you look at the final results, after a certain point, they impact your results. Like, for example, structure function, the method I have used, and I have digged in a lot, and I realized that when you look at the curve of structure function as a function of time, and it shows a break, and that break corresponds to some variability time scale. And if you look at if you take an evenly sampled light curve and introduce some evenness and look at that variability time scale by introducing different kind of unevenness, and in the end, what it turned out like you're not getting the same result. So that's one thing, and there is a paper about that. So, and the second thing is that I showed you an example, especially with, I'm very, very annoyed because of all those papers which took gamma ray light curves and don't even care about the red noise, underlying red noise processes. And they claim that, signal is periodic. And even for the same source, some paper says it's 13, some paper says it's 29. There could be multiple periods, but why like one method is showing you 13 days and one method is 29? If there is a real period, then every method should be able to detect it.
just a suggestion, you can check this Mexican hat method we are using to get low resolution public spectrum for sources with gaps and.
I think, I think Karma and the other thing, the other methods I haven't employed, and that's something I think I need to look into. Because that approach is not gonna be evenly sampled.
Okay, so I think we have to stop here. So let's then bring one of the speakers of the session again.